All right, well, welcome back for day two of AstroFest 2025. I think I know most of you, but there are a couple new faces in here, so I'll just quickly introduce myself. I'm Drew Desker. I'm the director here at Kopernik, and we've just had a great start to AstroFest 2025. Had a nice, relatively full house last night, and in great skies. And now we're continuing with the presentations we were doing. I think many of you got to see some of the solar observing resources we had outside there, and we will continue with our talks. And we're very fortunate again to have Zoe Lerner-Ponterio from Cornell's spacecraft planetary imaging facility, which we lovely always call SPIF, right? Because you're just spiffy people. I'm sure you've heard that so many times. But anyway, I will stop talking, and we're going to turn this right over to Zoe. And thanks again for coming down. And again, your wardrobe always is never the same every time she comes down, which is great. All right, thanks.
All right, thank you so much, Drew. Thank you for having me down again. I always love to come here for my talks. It's always a great audience with great questions. And so I'm going to say, like, if you have a question, go ahead and raise your hand, and I'll give it a pause, and we'll answer it. Hopefully have time at the end for some questions. So yeah, so I work at SPIF. I'm the manager there, and we do a combination of public outreach and technical support of planetary research. So one of my specialties is teaching people how to map things on other worlds, which is an interesting thing when you're using software that was very much designed with Earth in mind, and now we have to use it on other bodies that are different sizes, and in some cases not even round. So this talk, however, was inspired by Tompkins County Public Library coming to me and saying, would you like to do an art exhibit for the library? And I was like, okay, what would I do though? There's all these beautiful planetary images, but I always like to tell a story. And so I came up with the idea of, what if I put next to each other like the first image of an object taken next to the latest and greatest images, like show that improvement, that dramatic difference. And that sounds straightforward, and it ended up being a little trickier than I thought. First of all, I had to define, what do I mean by first image? Because, you know, we've been taking photographs of things in the sky for over 100 years. So I decided, okay, specifically space-based images. So it has to be an image taken by something in space, which typically means a spacecraft that is visiting that body. There's also a few other issues I ran into along the way, and we'll get to hear about them. And the number one question I get about space pictures is that what it really looks like? And my answer is always, no, it is not. Cameras are not human eyes. Okay, nothing in a camera is going to look exactly the way you see it. I'm sure we've all had the experience of trying to take a picture of a beautiful sunset, and then you look at your phone and you're like, yeah, the colors are not quite what I see. The same thing goes for space images. And so we try sometimes to make space images look as close to what you would see as possible. We sometimes will say things like true color, natural color, and that's our best approximation. But let's keep in mind that when we see things like these bright, beautiful pictures of Saturn, sunlight is 100 times dimmer at Saturn. So unfortunately, if you went to Saturn yourself, everything would look a little less impressive. I mean, Saturn would still be impressive, but everything would look a lot darker than I think you'd be expecting. And this is not going to do my normal talk of like starting at Mercury and working our way out. This follows a timeline. So we're going to go chronologically with our ability to image places from space. And so I'm going to ask, does anyone have an idea what the first world is that we imaged from space? Yes, Earth. Very good. All right, so Earth it was, and next I want to ask, what year do you think that was in? Heard some 70s, 50s. Yeah. All right, the 50s was actually correct. So this was taken on October 4th, 1957. It is, isn't it? Oh my gosh, I did not even realize that. Wow. I'm sorry, not. Oh no, wait, that was. Oh, I got that. That was Sputnik's launch. Hey, it's the Sputnik anniversary. Okay. That's what that was in my notes. No, okay, the slide says it correctly. So you would think the 50s, right? I was like, that sounds too late. Yes. White Sands Missile Range, October 24th, 1946. So what was happening in 1946? Well, the end of World War II had recently happened, and the United States had found itself suddenly in possession of some German V-2 rockets. And thankfully, there was someone who had a great idea. He said, what if we took out the warhead and put in a camera and launched it? The camera is much lighter, so maybe actually it can launch high enough to get into space. And it did. It reached an altitude of 105 kilometers. 100 kilometers is our definition for space. And took this first image. Then it fell back to Earth, and they had to recover the camera and develop the film. So I think, yeah, it's very interesting. The very first thing that we decided to do in space was take a picture of ourselves. And as a note, as far as like, is the Earth round? We see that I got that point there and this point here, but it does get higher. That is straight line, so the Earth's not flat. We checked. So even this first image from space, there's curvature. Yes. All right, so that was the first. We'll fast forward to some other firsts. This was the first image taken of Earth from another world. So this was the Lunar Orbiter 1, taken on August 23rd, 1966. And this image looks sufficiently grainy and poor quality, just like the kind of thing I'd love to put in that art exhibit to juxtapose against the modern images. But this was taken through the wide field camera of the orbiter. There was a narrow range that could take higher quality images. And so that image looks like this, which I'm honestly like, that actually stands up pretty well against modern images. And what was especially interesting about Lunar Orbiter 1 is the question of how it got the images back to Earth. I got asked the question, and there was a time I didn't know the answer to this question: how in the world did we get images beamed back to Earth before we had the concept of a digital image? Because at the time all this is happening, everything was photographic film. So how do we do that? Okay, so there's two ways you can do it. The roughly easy way is the way it was very often used, which was you didn't have a photographic camera, you had a TV broadcast camera. We had the ability to broadcast live TV television from the 30s. And so that is not the same as taking a picture, but it does create a radio stream that can carry that information back to Earth. And instead of a continuous video, we set it to basically take a series of exposures, but it still got delivered back to Earth in the same way we did live TV broadcasts. But not Lunar Orbiter 1. They kind of took it a step further. The camera there is actually a film camera. So it would, on board, had its little darkroom and developed the camera on board autonomously, and then scanned the negative for the light and dark, and radioed that signal back to Earth. Nowadays, of course, we all have the CCD camera in our phones, and then it's a more obvious answer to how do we get the images back. Another important first would be the first color image taken of Earth from another world. In fact, the first color image taken of Earth from out of Earth orbit. And this was taken with the Apollo 8 spacecraft, one of their high-quality color cameras, color film, December 24th, 1968. And it was taken by Frank Borman. Or so it was thought for several years. There's an interesting story of this. Frank Borman was interviewed, and he reported that he had taken this picture, and here's how it went down. They were taking images of the moon. They were scouting for landing sites. And if you listen to the recording of them talking, you can hear this conversation where you hear an astronaut say, "Oh, wow, there's the Earth coming up over the horizon. Look at that. It's so beautiful. I'm going to take a picture." And then you hear another astronaut say, don't take that picture. It's not on the schedule. Because they're only sent up with so much film, and they have very specific things they're supposed to photograph. And so Frank said, you know, I wanted to take that picture, but Bill Anders, who was a rookie, was like trying to stick to the exact things we were supposed to do. Now, I'm going to give it up to sometimes we misremember things. But there was something about this that didn't really sit right with a NASA historian. And that's if you know Frank Borman and his personality. Frank Borman appears to be the one person that went into space and didn't get the overview effect that they talk about. He will tell you he did a job. And that's all it was to him. So to have him get overwhelmed by something like this, I mean, maybe it was that moving. But an expert sat and listened to the recording again, and he knew the astronauts' voices, and he realized that it was the other way around. Bill Anders was the one flipping out, overseeing that Earth coming up over the horizon, and Frank was the one that told him, don't take that, it's not on the schedule. So maybe Bill Anders instead? So someone asked Frank about this again, and Frank, said, okay, no, I think I misremembered, here's what happened. A little while ago, I had the camera and I was taking pictures of the moon, and I saw something cool on the moon and I wanted to take a picture, and Bill Anders told me not to take it because that's not a scheduled take. And so when this happened, it was me jabbing him for what he had said earlier. And I was like, okay. But yeah, this became a whole thing for a while of trying to uncover who actually took this picture. And so another famous picture being the first image of the full phase of the Earth, seeing the entire Earth with the sun behind them. Apollo 17, December 7th, 1972. And perhaps because of all of this kind of confusion, this image is credited to the Apollo 17 crew. Not one astronaut in particular, though we do think that we know who took this. And let's see here, they think it was indeed Jack Schmitt. So you might know Jack Schmitt as the one and only scientist to have ever gone to the moon, a geologist who actually trained other Apollo astronauts. And so you'd love to be like, wow, yeah, I actually got to see him in person. I didn't get to meet him, but he was at a conference going to give a talk, and actually found myself in the elevator with him once. And there was this thing of I'm breathing the same air as someone who walked on the moon. But, sometimes you don't want to dig too much into your heroes, because Jack Schmitt also is a climate change denier. So, okay. Nobody's perfect, right? I haven't heard anything lately. I know that he publicly said that he disagreed with it as soon as 2018. I haven't heard anything more from him, but we'll see. So this really started the era of taking pictures of Earth from satellites. So that first person to have that idea to put a camera into space, look back down on Earth, was definitely onto something. He did, in fact, envision and predict what that would become, that we would start to regularly observe the Earth and observe things like changes in the weather and the features on the ground, and learning so much more about the Earth from that unique perspective. And so for my art exhibit, I picked a few of my personal favorites. This was taken by the Aqua satellite in 2010. That is an algal bloom off the coast of, I think, Norway. And then we have here by the Terra satellite, this is watching dust come off of the Sahara, starting to make its way into the ocean. And that's where it becomes storms. And of course, we can actually monitor things like the collapsing of ice shelves in Antarctica, also taken by the Terra spacecraft. We can save countless lives by knowing when hurricanes form and where they are tracking. This was Hurricane Florence in 2018. But sometimes in all of this science, we do also create art, even if that wasn't our intention. And this image was selected as the best photo of Earth from space in 2020, and it was taken back in 2001. And I could tell you the science of it, but I think we voted on it because it's just so beautiful. An honorable mention, this was the runner-up. And this was actually taken by astronauts on the International Space Station of a volcanic eruption in one of the northern Japan islands. So thinking back to the fact we took pictures of the Earth from the moon is indeed our next destination. So our beautiful pictures of Luna, the very first one, Not terribly impressive, sufficiently awful for my point of trying to put side by side, taken by the Soviet craft Luna 1, January 4th, 1959. Not a lot of detail you can see, but certainly not something that looks anything like the Earth. This one is also notable, taken by Luna 3. It's the first image we ever got of the far side of the moon. Now, there is no dark side of the moon in that there's no side of the moon that's always dark. There is always a bright side and a dark side to the moon in the same way that that is true for Earth. There's a daytime and a nighttime. But the moon does spin. It just spins at the same rate that goes around us. So it's like, you know, dancing with someone and you're spinning, you'll get dizzy, but you're always facing them. So we only ever see one side of the moon. And so I think this is an amazing moment when humans got to see something about the moon that, despite tens and hundreds of thousands of years of seeing it there in the sky, a side of it that had never been seen before. And also immediately noted that it did not look similar to the near side. There were not the huge mare that we saw. And that was quite a surprise for them. So on to the latest and greatest, we have Lunar Reconnaissance Orbiter, which has been orbiting, gosh, I think close to over 10 years by now. This is a picture of a collapsed lava tube. When you are on another world, like Mars or the moon, you do not have the protection of a magnetic field, and so radiation is very high. So one idea for living on these other worlds is perhaps underground, because rock will block a lot of radiation. So maybe live in a tunnel. We got these beautiful views. So many satellite views are like looking straight down, but Lunar Orbiter was able to orbit close enough to get like a, you know, a high angle view of a mountain at the center of a crater. The largest boulders on the peak of that are like about the size of like a large house, to give you some sense of perspective. And of course, we're still, even though we're studying the moon, yes, Lunar Orbiter will still take pictures of the Earth from the moon. I think we love seeing that. But Lunar Reconnaissance Orbiter is not the only one taking pictures. The Kaguya Japanese spacecraft took a video showing an Earthrise in real time, what you would actually see if you were in this spacecraft with the Earth coming up. But keep in mind, you only get to see an Earthrise if you're in orbit. Because again, since the same side of the moon always faces the Earth, if you land in one place, the Earth is always in the same place in your sky. So yeah, so Earthrises are not something that we get on the surface of the moon like we get sunrises here. All right, what do you think the next world I'm going to go to is? I heard of Mars and then of Venus. It's actually Mars. And this one, I absolutely love the first picture because it's this. And I've even shown some planetary scientists this, and they've been like, what is that? That is not the first image taken. And I'm like, well, I'm going to defend my position and say it is. Mariner 4, July 14th, 1965, was going to be the first spacecraft to send back images to Earth. Oh, I was like, did we lose power? No. Okay, we're okay. All right. So, of course, this was the days again. It's coming down as a live TV broadcast. And somewhere deep in the bowels of Jet Propulsion Laboratory, they're frantically seeing the data come by. It's raw data, so, you know, it just looks like gibberish to us. The computer knows what's going on here. And it was going to be several hours before the computer could process this into an image that could be viewed. But the engineers got really impatient. They wanted to know if the camera worked. So they decided they wouldn't wait. They said, let's go ahead and get it at least to the point where we have the numbers that show the brightness. And maybe then we can get an idea for the image. But what are we going to do with that? Well, one of them ran to an art supply store and actually asked for colored chalk, if you can see where his brain is going. Well, the art store owner was very like, we don't sell colored chalk here. We're a serious art supply store. I think he was thinking like for sidewalk chalking. He said, but I have these oil pastels, if you'd like those. And he's like, yeah, sure. They look like fancy crayons. It'll work. And the colors that he picked, you might think, oh, he picked oranges and reds for Mars, but he didn't. He just looked at them and tried to decide, where do I see like I can make a good gradient of bright to dark? and he saw that he had enough reds and oranges and yellows that he could probably make that. It actually was not in his head that Mars should be red because everyone was expecting this image to be grayscale, which of course it was. So then they proceeded to print out strips of these numbers and glue them to the wall and start doing a color by number. And kept on adding strips and coloring by number. So it was a movable wall, at least, but they were just gluing it right up to the wall. The press kind of caught wind of what they were doing and started like coming in trying to see what was going on, and they were like, wait, no, we're not ready for the press to see this. We do not want the press to think that this is how we process images, right? No. And so suddenly a lot of security, including people with big guns, came to say like, nope, no, everyone's got to stay away from this. And so that is where we got that first image. So I argue that that should be considered the first image because it was the first time humans saw photographic data of Mars. And eventually then the actual image came down. And so you can see they did a pretty good job. So here, of course, is the darkness of space. Here is the limb of Mars. And you can see like this big dark spot here corresponding to this one here. You've got some cloud wisps. In some ways, I think that their crayon one looks better. See more detail. All right, so what happened to this thing once it was done? It's up on this movable wall. It's glued. You can't take it off without destroying it. And they thought it was such a special thing that they cut it out of the wall and framed it. And then it was lost. People suspected it was somewhere at JPL, but as time went by, memory of this faded until sometime in the early 2000s when someone who was actually in the art department at JPL stumbled across it when going through somebody's lab or office when they retired. And so it was very special to me that when I went back there last year, that they had actually done the full display with everything, the actual case of pastels and framed on the wall, and there I am just thrilled and happy to actually have seen this physical piece of space image history in person. And so if you ever find yourself in Southern California, I highly recommend a tour of JPL because you'll get to see this. Now let's jump, of course, to the latest and greatest. We have the Mars Reconnaissance Orbiter, again, been there for, I think, now 15 years, taking absolutely gorgeous pictures of Mars. This is looking down at a dust devil. So those are like, you know, they look like tornadoes, but they're not dangerous. They happen in deserts here on Earth. But yeah, this is stretching up toward you in the picture mostly. And it's about like, let's see, 30 meters across. So pretty wide dust devil. Now, at first, this image looks like, okay, just another image of Mars, but I'd like to draw your attention, if you've got good eyes, you might be able to notice some lines. And yeah, if you zoom in, it's definitely not a natural phenomenon. Those are the wheel tracks of the Curiosity rover. They are 10 feet wide. That's the resolution we can see now. The high-rise camera can see down to 1 foot per pixel. So if you dressed in some high contrast, like bright green, and you laid down on the Martian surface, it would be able to see you. You would be a few pixels of something green. There is, of course, water on Mars. It's just all frozen at this point. And for the most part, it's concentrated at the polar ice caps. And again, I put this image in more for artistic than science reasons, because to me, these look like something that you would paint. All right, so now which world do you think we're going to go to next? Ooh, someone knows their history. Absolutely, Jupiter is next. All right, so the first spacecraft to visit Jupiter was Pioneer 10. And Pioneer's job was basically to demonstrate that you could get to the outer solar system and navigate to those planets. Because, of course, to get to the outer solar system, you have to go through something, don't you? Who knows what you have to go through between Mars and Jupiter? Asteroid belt. Okay. I often get asked, how in the world do we get spacecraft out to the outer solar system? How do we navigate through the asteroid belt? And the answer is, of course, we don't. We just fly straight through. Because despite being the most crowded place in the solar system, it is not at all what you see pictured in movies. Sorry to disappoint you. Spacecraft traveling through the asteroid belt have about a 1 in 600,000 chance of hitting something. We actually have to navigate very precisely if we want to rendezvous with an asteroid, which all spacecraft that have gone through the asteroid belt usually find one that's enough in their path that they can actually do a flyby. So one thing that I do back in Ithaca is I help the Science Center there with their Sagan Planet Walk. This is a full 1 to 5 billionth scale model of the solar system. It does distances and sizes, which is really cool. The sun is at the Ithaca Commons, about the size of a basketball, and then Pluto is at the Science Center, which is about 3/4 of a mile away. So it's a nice walk through part of downtown Ithaca. And I get to write the plaques that go on the monuments. And when I got to redoing the one on the asteroid belt, I got curious, did the math, said what would be the asteroid belt on this scale? Because all the other ones have how big the planet would be. But how do you do that with the asteroid belt? So I did the math. And on that scale, if you gathered all of the material in the asteroid belt into one object, it would be the size of a grain of salt. And you break off 1/3 of that grain of salt, and that is the dwarf planet Ceres. And you take the other 2/3 of it and you crush it up into millions of pieces, and then you sprinkle it over an area the size of 3 football fields. That's the most crowded place in the solar system. So yes, we just go on through. But Pioneer was the first to demonstrate that that actually is what happened. Here's where I really ran into a big issue, was trying to find the first image, because Pioneer 10 and 11 are so old that they predate, of course, digital imagery and also proper archiving. In the beginning, NASA, I think, was just very much like, get it done, release it to the press, and once everyone had their fill of it, it just did not get preserved. And so as far as NASA can tell, no, we do not have a full archive of all the Pioneer images, which is rather sad. It also makes it rather difficult to decide which of the ones we do have is the first. So we start taking images before we really are even up close. We're testing out the camera. Are we heading the right direction? So this is generally considered the first 3 shots that we get of Jupiter as we are approaching. And eventually you get to a point where you can start to see the cloud bands. And then you clean these images up a lot, and you can process it into something that looks like this. So this is an example of about the best quality that Pioneer 10 could do. And the flyby was in early December in 1973. Now, of course, this was then followed by the Voyager spacecraft. That's what Pioneer did. It laid the groundwork for the Voyager craft to go, and boy, did they bring this into real view. 1979, Voyager 1 flyby of Jupiter. The world went crazy. I do think, I don't have a favorite among the solar system, but I do think Jupiter's one of the more photogenic planets, at least in the colors that we can see. And as beautiful as that is, got shown up again recently by the Juno spacecraft, which has been orbiting since 2015. It's now completed its entire mission of studying Jupiter, but it's still working, so now we're using it to check in on Io, the closest moon that's all volcanoes all the time. And I have some people that work on Io that are very thrilled that they're getting these up-close images. This is an up-close of that great red eye. And so this is the part in the talk where I like to just say, like, let's just look at Juno images of Jupiter, because I do think that they are some of the most beautiful images that we've ever taken in space. Personal opinion. I did recently get to do another art project. The Syracuse Symphony was doing a performance of The Planets by Holst, and they said, we'd like images up on a big screen above the orchestra, and so I got to put together that, and I had a fun time focusing more on art than science. And when I was trying to pick among all of these images what to put up there, I was listening to that planet's movement on repeat softly in my headphones to try and subconsciously inspire myself to choose images that fit the style of the music. If you ever heard Jupiter, it's very happy and excited, and so I tried to choose very colorful images. And so you might think, okay, well, these are really like way better than that Voyager 1 image. But there is an artisticness to it, because Juno's camera, JunoCam, was not a scientific camera. It was literally a tourist camera that they slapped on at the last minute and said, how about we just make the raw images available to the public and let them have at it? So all those images you just saw were processed by people, not scientists or NASA employees, just people out there who wanted to have a fun time of it. If NASA likes your image, they give you a credit at the end of the name, so you can get your name at the end of processing that. So you can go to the Juno website, have your hand. And you can actually reprocess Voyager 1 in the style that people are processing Juno, and I don't know, it holds up pretty well. Where do you think we're going next? You'd like to think that, wouldn't you? Venus is actually next in the timeline, because between Pioneer 10 arriving at, well, not Pioneer 10 went on, Pioneer 11 arriving at Saturn, we actually got to Venus finally. So this is generally one of the first images taken of Venus, Mariner 10, February 5th, 1974. This is post the Venera probes, which were about trying to get to the surface, so they didn't carry cameras to take pictures from space. So Mariner 10 was actually the first to do that. And then, of course, we then followed it up with Magellan, which was a big mission, ran from 90 to 92, was actually launched from the space shuttle, not straight from the ground. And this image gets passed along a lot, and in fact, if you Google image Venus, you're going to see this a lot. And I hear a lot of people even say, well, this is what Venus looks like with the clouds removed. And this is often used as like a default image of Venus. And as amazing as this image is, I don't like that that's the one that people are seeing primarily, because no, that is not what Venus would look like with the clouds gone. Venus is not bright orange. This is an image in radio waves. The clouds are too thick for the light we can see to get all the way to the ground. So what Magellan did was use radar. Emitted radio waves, went through the clouds, hit the surface, bounced back, and were measured by the spacecraft. So this was taken in a color of light that you cannot see. So the only way that you can see it is if we assign a color we can see to represent that. They could have picked any color. They picked orange, I guess, because Venus is very hot, so they thought doing green would be weird. But yes, this is not a true color image of the surface of Venus. The ground on Venus is very volcanic rock, so it's like gray, brownish, very dark rock, not bright orange. Now there's two different modes you can put that spacecraft in. You can point the spacecraft straight down, send the radio waves down and have them bounce straight back up, and by timing how long that takes, you can get altimetry, you can get the terrain. So you can build these beautiful three-dimensional views. But again, the rocks aren't bright orange and the sky is not black on Venus. Another mode you can do is to be at an angle and send the radio waves down to the surface and then see what bounces back at an angle. That's where this orange data is coming from. And it tells you about the texture of the surface. So if you have a very smooth surface and you send that radio wave down, like a mirror, it's going to mostly bounce back in the other direction, and the spacecraft here is not going to really see anything coming back. So dark generally means maybe a very smooth surface. However, if you were to hit a surface that's got angles all over the place, then some of the radio waves would bounce back in the direction because they bounce off in all directions. So bright things represent a rougher terrain. And I could go deeper into the science of what light and dark means in radio wavelengths, but yeah, this is not Venus without the clouds. This is also exaggerated, so things are not actually that dramatic. So back to those clouds, because when I was listening to Holt's The Planets, the movement on Venus, if you ever listened to it, he was thinking the mythological Venus. And so the Venus piece has this beautiful, wispy, beautiful, soft music, not at all seeming to match Venus with the hottest surface that would melt lead and crushing air pressure that would make your submarine completely collapse like you were a mile deep in the ocean. So a lot of times if you watch videos where they want to put music to Venus, you'll actually hear them take Holt's Mars suite, which is dramatic God of War, and they'll play that against the Venus images because it fits the scientific knowledge a little better. But I was listening to the Venus suite, and I decided that where that fit was the cloud images. And thankfully, we have a lot better cloud images than this now, because the Akatsuki Japanese spacecraft just recently spent several years at Venus and was studying the clouds and produced really beautiful images of Venus. And that is taken in ultraviolet light, the stuff that would cause a sunburn, but not a color you can see. So again, falsely colored, not as your eyes would see it. And this is a picture taken of the nighttime side. And for this one, we went the other direction past red to infrared, which we generally sense as heat. So this is the heat coming off the clouds on the nighttime side of Venus. So I've just told you about two different pictures of Venus, one taken in ultraviolet, one taken in infrared. So neither of these were taken in colors you could see. And so a lot of people, they want that. They want to know, yeah, but what would Venus look like to me if I went there? And so I dug and dug trying to find a true color image of Venus. And I found one. And it was taken not by a Venus mission, but by Messenger on its way to Mercury in 2007. Would you like to see what Venus would actually look like to you if you went there? Sorry. Yes, that is Venus to our eyes, and that's why we don't take those pictures when we have a mission to Venus. Above those clouds that we've all seen, there's actually a hazy layer that reflects most of the visible light. That is one of the reasons Venus is so bright in our night sky. It is often the closest planet to us, but it's also extremely reflective in the light we can see. But that's bad for science because we'd like to see past that. So speaking of Messenger, yes, the next place that we are going to go is Mercury. And the first spacecraft to visit Mercury was Mariner 10 in 1974. This was, again, one of those first images as it approached, and this image represented about the best we had at that time with ground-based telescopes. Not a lot of detail, but thankfully when Messenger got there, we got a huge upgrade. And this picture of the limb, you can see again, is showing you that Mercury is extremely cratered like the moon. And for that, some people think that even though these are like kind of pretty, they're also kind of boring compared to like Jupiter or Mars. But keep in mind that craters are actually extremely important to understanding the history of the solar system. If you have a body like the Earth that's extremely active, we don't have a lot of craters, not because things don't crash into us. The atmosphere does help block some stuff, but mostly it's because our surface is constantly being remade. We've got earthquakes, plate tectonics, volcanoes, we've got oceans and glaciers and all this stuff changing our surface, and craters quickly get erased. If you ever have a chance to go out to northern Arizona and see Barringer Crater, I highly recommend you do it. It's the best preserved crater right now on the planet Earth. So if you really do want to see an Earth crater looking really pristine, go see that one. So yeah, a lot of craters, but that also means this is not an active world. Mercury has not had a whole lot of action going in the 4.5 billion years it's been around. Not nothing, it is slowly shrinking. But yeah, this is a time capsule. This is a window for us to see what was going on in the early solar system farther back than we could possibly see by looking at the Earth's surface. And I do have some personal favorites of craters on Mercury. This is the crater Balanchine, named after the famous ballet choreographer. You see, with each of the planets and any of the moons, all of those, we adopt a theme for naming craters. And Mercury's theme is craters are named after artists, musicians, writers, poets, sculptors, people that contributed to the culture of our world. This one they picked for Balanchine because this blue streaking coming off of it reminded someone of the long blue tutus that the ballerinas wear in his serenade movement that he did. So, having been a ballet dancer, I'm like, I like this one. The other one that's a personal favorite is Rachmaninoff crater. What's so big about that? Well, if you know Rachmaninoff, he was a composer. And I am his first cousin, fourth removed. 3 times removed. Oh, we shared the same great-great-grandparents, I think? Yes. So this is probably the closest I'm ever going to get to having something sort of named after my family in space. So, I don't know, maybe I'll get a Pontario on there someday. If you want your name on something, discover a comet. That's the easiest way, because they name comets after the people that find them, so. But this is one of my favorite pictures of that Messenger took of Mercury. Looks nothing like any of those other ones, does it? Again, there's some false coloring here to bring out the details, but yeah, what are we looking at here? We're still trying to figure it out. I love showing images and people are like, okay, explain everything that's going on in here. And I'm like, yeah, we still don't know. There's still papers coming out trying to describe what these hollows mean. We think maybe some kind of sublimation coming off the surface, but I also just think it's a really cool, beautiful image that just doesn't look like an image you expect to see of Mercury. Where are we going next? Finally going to get to Saturn. All right, so again, we're going to run into the same problem that the first images are from the Pioneer missions, in this case, Pioneer 11. I don't have the full series, but this was one that got released, so this has been processed, it's been even colorized. We see the moon Titan right down there, another something with zipping across there. All right, so that was Pioneer 11 in 1979. And then there's a big gap in taking pictures of Saturn up close until we got to the more recent Cassini mission, so we'll check out the upgrade. Yeah, that's a nice side-by-side. All right, so that was taken in 2008, so pretty recently. All right, Saturn sometimes doesn't get the credit that Jupiter does. People think that Jupiter looks more dramatic, but I think Saturn has its own drama going on, such as, yes, storms. Not one big red spot like Jupiter has, but seasonal storms that we've seen lightning in. So maybe it's some sort of like huge thunderstorm. And what happens is, as it forms, it travels around, leaving this wake behind it, and that wraps all the way around the planet and comes back around to that side. And soon after this kind of eats its own tail, it fizzles up. And usually the lightning is concentrated at the most active part. Now, we know that these happen seasonally. The problem is we still don't know exactly what kind of seasonal changes, because sometimes they're in the northern hemisphere and sometimes they're in the southern hemisphere with no discernible pattern that we have found yet. So that's still an open question. But I also think that the less dramatic clouds of Saturn do have their own kind of beauty, and I love that this picture is like not all these garish colors. It's very serene. You can make a little bit of shadowing right here, so it gives it a bit of a three-dimensional feeling. And then, of course, those rings. We got some amazing pictures of the rings, and we discovered something really interesting about why the rings are so well defined. And that's because they are shepherded. The tiny moons that orbit in the gaps between the rings and just outside of them are called the shepherd moons. And the gravitational wake as they pass by keeps those rings in check, keeps them lined up nice and neat. But we do think that Saturn is losing its rings. So in a couple 100 million years, the rings may mostly be gone. We also think that maybe it's not always had rings, and that a few 100 million years ago did not have these rings. So it's possible that at the dawn of the age of the dinosaurs, Saturn was not Lord of the Rings. So we're starting to understand that rings are not a static thing, that rings might have this dynamic relationship with moons, because Saturn's rings are icy and these close moons are icy. So it might be this cycle of moons breaking apart to form rings, and then rings eventually globbing together to form new moons. And there are other worlds that we think we see this happening in, and in fact, this probably happened with Earth. When the moon was first forming, it hadn't come all together, and so we briefly did have a ring until we got the moon. Mars is probably someday going to have a ring, because the larger moon Phobos is absolutely doomed, is orbiting a spiraling in orbit. It is now so close to Mars that it orbits 3 times a sol, which is a Martian day, only slightly longer than ours, as opposed to our moon that takes 4 weeks to orbit. It will not crash into Mars. What will eventually happen is it gets close enough that the tidal forces, the difference between the pull on the 2 sides, will rip the moon apart, and Mars will get a ring. Another interesting feature of Saturn that Cassini discovered was at the North Pole, the rings of the clouds are all circular until you get right here. There's a hexagon. And it changes color with the seasons. So these are approximately true color images, and it just stays there. And we're not exactly sure why. Why suddenly out of all these circles do we get a hexagon? And I try and stay up on these things because I work with some of the prominent scientists doing this work. And just last June was an alumni weekend, and I had my magic planet, my globe that turns into anything I want it to. And I was showing the hexagon to somebody on that globe. And I was about to say, like, we still don't know what causes it. And then I realized who was standing right next to me was Dr. Phil Nicholson, one of the experts on Saturn and the rings. And I said, hold on. I turned and said, Phil, how are we doing on understanding that hexagon? Have we made any progress? And he's like, yeah, no, not really. I was like, okay, good. I can still say that we're not sure what this is. Now, of course, we also take pictures in the colors we can't see. So here's a very interesting shot of Saturn, a not true color, but we got infrared light. So on this side, we see mostly infrared light that's bouncing off of the clouds coming from the sun. But then where the shadows are filled in with infrared light that's just coming off of the heat of Saturn's clouds without the sunlight. This is another false color. So you see, we're going to color things. People ask, what's the color differences? Composition, temperature, pressure, things like that will change the color. And at the center of that hexagon is called the rose of Saturn. It's a huge storm. Pretty much every one of our celestial bodies that has an atmosphere has a polar vortex at both ends. But when you go to the South Pole on Saturn, there is a polar vortex, but no hexagon. That's where the rub is any explanation you give for why there's a hexagon has to also explain why there isn't one at the South Pole. We have polar vortices, but Earths do something really kind of interesting. Oftentimes we have just one polar vortex at the North Pole, but sometimes it splits into multiple polar vortices, and one might then wander off and come and visit places like New York State. So if you hear on the weather saying a polar vortex is coming, that's what they're talking about. Yes, one of Earth's polar vortices went on a little vacation south for a while. And now we kind of get to the moons of Saturn. There are how many moons in this picture? Who can count them? I was like, four, wait. Yeah, so the perspective kind of ruins you, like, this is a moon, not Saturn. Like, we put the rings there and then you just ignore this because it's like, yeah, that's the planet. So yes, there are 5 moons in this picture. For the most part, Saturn's moons are all very icy. There's a few medium-sized ones and then a lot of little tiny ones. It was always, as I was growing up, that Jupiter had more known moons than Saturn. Like, the 2 numbers were gradually going up, but Jupiter always had more, and that seemed fine because Jupiter was bigger. And then a few years ago, I guess the Saturn people had it with this, and they worked really hard to discover some more moons. And they discovered over 60 new moons in one data release, and that shot Saturn way past Jupiter. Then they started discovering a lot more about Jupiter. They wanted to hold on to that title, so then they found even more. So now I think Saturn's moons count at like 160. So they don't want to let go of that title. We'll probably continue to find more around both of these planets. But there's one moon in particular that kind of sticks out as not like the others. And that's the dark one in the background there that just seems to be fuzzy. And we don't see any features. And there that moon is sitting in front of Saturn. That is the largest moon, Titan. It's the second largest moon in the solar system unless you want to include the atmosphere, which is the only moon with an atmosphere, and then it is the biggest. I say no, we don't do that. No, you don't get to add the atmosphere. If we do, then the atmosphere of Pluto, when it's at its closest to the sun, gets to be about maybe almost the size of the Earth. So then is Pluto bigger than the Earth? I don't think so. It is bigger than the planet Mercury, though. This is a moon that tricks us even as we're studying it, and we often slip up and say planet, even though it's a moon. So for years, this was all we got from it. So our first picture ever of Titan came from Pioneer 11 and took 4 pictures. And I only included one because they all basically look like that. Confirmed what we had seen from the ground, which was that it's orangish yellow. But not a lot of details. When Cassini arrived, we did start to get a clearer view. We saw, okay, there are features on the surface and there are defined clouds. And so yeah, that atmosphere is really quite interesting. It changes from this orange to this haze that's more blue. Like our atmosphere, it is mostly nitrogen. Ours is about 70% nitrogen. This is 95% nitrogen. And that right there is a storm cloud. Storm cloud, that'd be interesting. So suddenly we were about to get our first ever view of the surface of Titan, which people had debated about what was going on under all that haze. So on January 14th, 2005, the Huygens probe that had been released from Cassini the Christmas day before that finally descended through the atmosphere. And the very first images as it was going down on the parachute came down, and wow. What does that look like? It looks like rivers, right? Flowing into each other. There are no rivers on any other world other than Earth in the solar system. As it descended, it saw this terrain and continued to see these river-like features. And when it finally landed, took this one picture from the surface, and we see very rounded pebbles that are maybe about half the size of your foot, like you would find in a floodplain or a riverbed. So what's going on here? First of all, I'm going to challenge to ask you, can we call these rocks? Because you know what they're made of? Ice. The surface of Titan is ice. And so is it still a rock? What defines a rock? Is it what it's made of, or physically what it's doing, breaking off of the surface of a world and loosely roaming around on the surface? When you start getting to alien worlds, your words for things start to get a little tricky. So what's going on here is that if you use infrared to go through the clouds, you see these features at the North Pole that are glinting, like they're shining. And it turns out that those are enormous lakes and seas, rivaling the size of our Great Lakes. But the surface of Titan is almost negative 300 degrees Fahrenheit. So that liquid is not water. It's mostly methane. The other 5% of the atmosphere on Titan is methane, and the temperature and pressure is just right so that methane can condense into a liquid and rain, so that that storm cloud is raining methane. So this is the only other world where it rains other than Earth, and that rain will collect into rivers and flow into lakes and seas. So this is the only other world other than Earth with liquid on the surface and a hydrologic cycle happening. Can we call it hydro? Because hydro means water. Are we okay saying that hydro actually means liquid? I had somebody who was studying this, and they referred to the methane, liquid methane that might be underground as groundwater, and I was just like, what? No, you can't call it groundwater. He's like, well, ground methane sounds weird. I'm like, I don't know what to tell you. I do the public outreach. I can't go out and say groundwater. So yes, there's ground liquid methane as well. Now, the problem with these is this is radio data, and Titan has a real hard time with radio. It's the only thing we can get through, and it has this very speckled appearance. So if you wanted to make it look better, you can process it to like, ooh, look smooth, but don't show a scientist this picture. They'll cringe, say like, well, that is just not scientific at all. You just made it pretty. But this is a talk about pretty pictures, so I included it. All right, now we get toward the outer solar system, and it gets a bit hard because starting with Uranus, I chose that as the first picture taken of it by Voyager 2, November 6, 1985. That was the start of the imaging sequence on the approach. So then trying to go from that to the best, most modern picture of Uranus is just a little while later, same spacecraft, Voyager 2. Because Voyager 2 is the only spacecraft to have flown by Uranus. So not a whole dramatic difference between first and best image. This looked pretty boring. And that was a bit of a downer after the Voyager spacecraft had visited Jupiter and Saturn and seen all this dramatic stuff. And then they got this image and they're like, oh man, how are we going to sell this as exciting? You know, okay, it's tipped on its side, there's rings, a little bit of cloud right there. So they're like, okay, we're going to make this exciting. We'll get all set up to have the big press conference to release these images. And the press conference, unfortunately, never happened because that same morning, the Challenger space shuttle blew up on launch. By the time they had come back around to this, nobody cared. And so this didn't get a lot of press on it. But if you use imaging processing, you can show that there actually is structure here. Again, that the human eye cannot see. And with modern processing, you can go even further. So even though this image was taken in 1986, this was reprocessed in 2014. And remember, I pointed to that bright white cloud. There it is in this feature. So again, is this true color? No, but it shows that there is structure there. So yes, there are cloud bands. They're just hard to see. But Voyager 2 is not the most recent space-based images because, of course, we have space-based telescopes. So then I had to ask myself, am I allowed to include a Hubble picture? Hubble's not at Uranus, but it is in space. So I decided, okay, yes, I decided my rule was images taken from space of things. So even though this is an Earth-bound telescope, I decided to include it. So we can almost get better images. And this one can't be part of the art exhibit, even though it's probably one of my favorites because we see here clouds and storms blowing up, but it was taken by the Keck Observatory, which is on the ground. So not a space-based image. We're hoping for more images with a mission soon dedicated to go visit Uranus. Run into the same problem with Neptune. So this is our first image of Neptune taken from space by Voyager 2 in 1989 on its approach. The thing I find really fascinating about this image, is kind of impressive, is this was taken at a distance twice as long as the distance between the Earth and the Sun. And you still can see details. And from Earth at this point, Neptune was just a blue ball. They hadn't seen a lot of features. And of course, just a few months later, we actually get to some of the best images ever taken of Neptune in Voyager 2, showing that it did have storms. Some thought the dark spot was similar to Jupiter's red spot, but it turns out dark spots come and go on Neptune. And did have these cloud bands. That's just really pretty. So Hubble has also imaged Neptune, but we're now getting to a distance where no, Hubble cannot rival the up-close images. So this is the latest and greatest. When I made the art exhibit it was, but since then, we've also had JWST take an image of Neptune. But keep in mind, this is not visible light. JWST is an infrared telescope. So again, we're looking at a color that our eyes cannot see. And now we've made our way all the way out to Pluto. First space-based image of Pluto. sufficiently awful for my art exhibit, right? This was taken by Hubble in 1990, so this was before Hubble got its eyes fixed. You might say, why did they bother taking a picture then? Well, they said, in the meantime, while we figure out how to make glasses for this telescope, let's test the other systems. And so instead of tracking it on a star, which was totally, you know, the background stars are stationary basically to us, they said, let's point it at something that's moving with respect to the stars, but not too much. So it has to take an image of Pluto, right? It has to have a very long exposure, and we have to make sure that the telescope is actually continuing to follow the motion of Pluto, which for that test it was. But that means that this was the best we could see of Pluto at that time. All right, then Hubble got fixed. So summer of 1994, they went through a new campaign and started to see definite light and dark spots on the surface. And in 2010, we were getting to the point where we had a little bit of color, and again, some features on the surface. So we were about to get one of those dramatic and sudden upgrades in that I grew up being told that Pluto probably looked like Mercury, right? Or the moon, heavily cratered, cold, dark, it's tiny, it's only as wide as like half the continental United States. That was the artwork that we saw in every single book that talked about Pluto. And then everything changed, because in 2015, in a matter of days, we suddenly got a view of Pluto that did not look anything like what we thought it was going to. Not completely covered in craters, huge ice sheets. This is the edge of that famous heart, with dunes on them. Dunes, like sand dunes, only the sand's made of frozen methane, so cold at this point, frozen nitrogen. And mountains, as high as the Rocky Mountains. This world is active somehow, and we are still trying to figure out how. So here you can see those dunes. There is an atmosphere, and this is my favorite picture, though. This is looking back at Pluto because it was a flyby. We were going too fast to go into orbit, and so as we're passing, we took frantically pictures, and this was one we looked back as we said goodbye. And then we have to come to the end of our talk talking about the farthest object that we've ever visited, at least with a spacecraft. So our first view of this particular little world, 2014 MU-69, taken by Hubble Space Telescope in 2014. After the Pluto flyby, the New Horizons spacecraft was still working, and we said, okay, we're heading into the Kuiper Belt. Is there a Kuiper Belt object that is sort of in the direction that we're heading that we could pass by? And they found one, and this was a perfect candidate. And so even though the mission to Pluto was over, we all waited in 2019 to see the first ever Kuiper Belt object up close. And once again, not at all what we thought we were going to see. So New Year's Day 2019, I was glued to the television to see this picture, and we named it Arakoth, which is a word in the Powhatan and Algonquin Native American languages that means sky. And so that's where we finish. This is the farthest object we've managed to get detailed images of from Earth, and probably will be for quite some time, because beyond this is just more tiny little red rocks, and we don't think another big planet, but can't rule it out either. So, any questions? Yes, so we think that this is what's called a soft contact, where they crashed into each other but slow enough that they didn't bounce off of each other again. So I think of this kind of like when you stick your tongue on a cold flagpole and it sticks to each other because it's very cold out here. So you had the heat of the impact melt the ice, which these are very icy bodies, but then refreeze before they had a chance to bounce off of each other, and now they're stuck together. Now what was really funny is we said this looked like a snowman. Right? So we just assumed from this picture that these two halves were round. But then as we passed by, we don't have a straight up image of it, but we measured things. It turns out that both of those are actually sort of flattened. So the top one's more like an M&M, and the bottom one is more like a Nilla wafer. And so the joke went around of like, Arakoth saw this spacecraft coming, had never seen anything like this. It got scared, and like any animals, like it puffed up and showed its big side. Like, look at me, I'm big, but then it was actually like really skinny on the side.
Well, we do have a question actually from the chat.
Yep.
Captain Crunch asks, wait a second, where is it? What are the sparkly parts in Jupiter's atmosphere?
Parts in Jupiter's atmosphere.
I'm wondering if maybe you could go back to your Jupiter image or images.
You know what the easiest thing is to just come out of this and go back in. So looking at these images.
Sparkly parts.
Maybe referring to like in this one when you can see down here. And I'll do it on the pointer so people online can maybe see. Can they see this? So below that red spot right here. Find another one. Ooh. So yeah, like right here too. So these are places where clouds have actually like popped up above the main cloud deck. And so you're seeing the bright white clouds and a little bit of shadowing. And I said this camera was a pure tourism camera, right? They weren't going to study Jupiter's outside. The Juno mission was to study Jupiter's interior. So why put a camera on there if you're studying the interior, but then said, you can't go to Jupiter and not have a camera to take pictures of things. And so these were purely to have fun with. And yet, you give scientists data, they will do something with it. And I worked with a student a few years ago who was measuring the shadows cast by those clouds to determine their height. And of course, you have to ask where was the spacecraft and where was the sun and where was the surface and do all the three-dimensional trigonometry to figure out what that shadow height tells you about the clouds. So scientists will always use any data that they get.
All right, we have another. Captain Crunch asks also, I wonder how many planets have methane on them that we know of.
So obviously I mentioned Titan, but there is methane in the clouds to some extent of most of the outer planets. Methane is one of those that likes it cold. And there is also significant methane in both Uranus and Neptune's atmospheres.
All right. Any questions here on site?
And I mentioned methane on Pluto as well, but it's frozen there.
All right, well, Zoe, once again, thank you so much. Again, if you do have any other questions, I know Zoe will probably hang for a little bit. And we're going to take a little bit of a break. And then one of our Kopernik Astronomical Society members, Patrick Manley, is going to do sort of a talk about those rocks that come out of space, meteorites. And he's our meteorites expert. So it's 10 after. Let's give ourselves a 5-minute bio break if needy, and then we can reconvene. Patrick, are you going to be in here? Yeah. All right, we'll be right. So we'll be back in about 5 minutes.
Excellent.
Thank you.
Thank you. Thank you.
All right, well, welcome back. We're day 2 of AstroFest 2025. We are now moving to another topic in space, meteorites, and or as this as the slide shows, rocks from space and what they are and what they're not. So again, we're very fortunate to have Patrick Manley, who's part of our Kopernik Astronomical Society member, and a meteorite aficionado. And so whenever anybody has a rock of any sort, I say, okay, you got to talk to Patrick. And so, Patrick, over to you.
Oh, great, thanks, Drew. So I'm not an aficionado. I'm an addict. Once you start collecting things like this, it's really hard to not collect them. But they're really excellent specimens. I'll be handing some of them around. I brought a couple boxes of rocks here, and I'll be handing some of those samples around for folks to see what they're like. You don't really get a sense how they're different from Earth rocks until we talk about it a little bit and then hand it. First 20 minutes or so, I'm going to do a presentation, and then we'll focus more in on the samples after that. So there it goes. Who here has seen this from 2013? This is in Russia in a town called Chelyabinsk, not much unlike Binghamton. It's about the same size. And basically, as this guy's driving to work or wherever he's going, he's got this thing happening in the sky up there going overhead. Leaves behind this really weird cloud. You see all these little fragments breaking off of it, and they continue to go along. And it was a really impressive activity, you know, when it happened. It was all over national news and everything like that. A lot of people didn't realize when you look at that, what you just saw, it doesn't look like much, right? It's just this thing going across the sky. It could be a lot of different things. This is just another view of it too from the other angle, and it's coming in again. Looks wild and crazy and weird from a distance, but it doesn't look like that big of a deal. But, and I don't know if we have, yeah, we have sound. Okay, good. But there's that cloud, right, going right over. And it was actually a significant event. It injured somewhere around 1,100, 1,200 people. These people are going like, what is going on? The guy with the cell phone got knocked down. You can see his hand flopping around. You know, so it was enough to knock him down. Windows breaking all over the place, all over the town. So there's actually a shock wave that comes with that, right? A significant shock wave. And if you were at the heart of the blast, it would have been something like 30 times the blast at Hiroshima, where it occurred. The shock wave is just air particles moving due to that blast. The one thing you really have to think about is it's, you know, this picture shows it really well, its flight path. It's going this way. Imagine if it had gone this way, right? Down. So these things are significant. You can kind of see, I'm assuming this is, nope, that's not laser. What was that? You can see here on this one that it's, you know, it's a pretty good sized rock. It's not the biggest ones we know of. Zoe just talked about Barringer Crater. It's one of the most well-preserved craters on Earth. And she said if you ever can go there, you can go there. That's about the size of the meteorite that caused Barringer Crater. So it's pretty good sized rock, right? We didn't know it was coming. Kind of an interesting thing. As we move forward in time, we got to have a little better sense of some of these. We'll talk about Tunguska in a second. And this talk is going to be on meteorites. There it is. This is called a strewn field. And so this path is the path that the meteorite took as it went. The larger particles go further. The larger the mass is, the further it's going to go in that strewn field. The smaller ones are going to break off and fragment out and fall down to the surface. A lot of people found a whole bunch of them out in here. The folks who really went hunting for them out in here, they found like really massive ones, right? Really good sized rocks. So it's really important to understand that when these things fall, we're going to talk about some of the myths and some of the facts about how these things fall, because people get a little confused about that from time to time. There's a couple resources out here. I'm going to cover 2 of them that you can watch to see. These fireballs are happening all the time. These are just random ones I grabbed over the years from the Fireball Network that NASA hosts. It's kind of neat. You can go out there and see them. The Fireball network actually has 3 cameras per cluster, and they can actually use the 3 cameras to calculate where it's going and where the strewn field might be, if it's a big enough hit. Also, the American Meteor Society is another place. They have all sorts of videos and photographs, and up to, like, if something happened yesterday, it would be on their website. So it's kind of fun to just go out there and visit once in a while and watch all these. Some of them just fall and they flare out like the ones you usually see. Sometimes they light up the whole sky. It's kind of interesting. So I really recommend that resource, as well as I mentioned the Fireball network. The Fireball network is kind of cool because it, like I said, you can use the data from the different cameras to figure out exactly where it was going, how fast it was going. You can tell by the magnitude of the flare out that it was a big rock or a small rock. And we'll talk a little bit more about that in a second too. We have to do some house cleaning because everybody who doesn't study this field has different meanings for these words. So it's really important that we get kind of down to the right wording when we're talking. A meteoroid is something that's space traveling, maybe near Earthbound or an Earthbound mass, but it's not quite, hasn't entered Earth's influence yet. We call those meteoroids. A meteor is one that the mass enters the Earth's atmosphere and it begins interacting with the Earth's atmosphere, and it could be a superheated gas, and we can view it and observe it visually. But it's not a meteorite until that sample actually lands on the ground. Once it hits the ground, now it's a meteorite. Meteor showers, they are small particles that are mostly meteors, but you just get a whole bunch of them. And so you see a lot of these things passing through, and you see all the meteors passing through, making, some of the gas burns. We can see those visually in different colors and different lengths and periods of occurrence. So as some of the other house cleaning house meteor showers, so you hear about the Perseid meteor shower, or almost never lead to meteorites. They're usually very small dust particles that don't make it through the atmosphere. Typically, the shooting stars, they tap out at their largest, the size of marbles, and that's not big enough to make it through the Earth's atmosphere. It'll burn up. Most burn up before they can enter the atmosphere, even, like as I just mentioned. And this guy, you'll see the video. I'm not sure, is it playing? This one's a hard one to tell if it's playing. But there will be like a little drifter that goes off across there. Sometimes that one fails. I apologize about that. But even most of the ones that we see that are sizable enough to have masses that come through the atmosphere and make it in and land to be meteorites, probably the normal largest is like fist size. They're not usually giant things that hit the Earth and cause all sorts of problems. Oh, there it goes. So something like that may have been a fist-sized rock, but you can see how it's flared up and it's holding. Do you see that? It's getting bigger, and then it pops. They call that a bolide. And that's when you're going to get maybe something that's like a fist-sized rock, is something like that. A fist-sized rock, not multiples like the first one we looked at. So there, again, they're not going to happen during a meteor shower. The fireballs only, typically only burn for maybe 10, 30 seconds, something like that. You saw that Chelyabinsk was a massive rock, and it didn't even burn for 10 seconds, right? So, you can kind of get a sense of how they are. They do not burn all the way down to the surface. The interactions only, just like you see with the spacecraft coming in, it's only while it's going through the atmosphere is when it's interacting in a heat-type manner. So when they hit the ground, they almost never have any heat signature to them at all. They're usually cold to the touch, actually, at that point. They're not laden with different levels of radiation, things like that, at least none that we've seen to date. And in the US, this is kind of interesting. In the United States of America, ownership of a meteorite belongs to the landowner where the meteorite landed, not the person who found it. It's considered mineral rights, which is kind of an interesting little fact. And a lot of the other countries, it gets a lot different. You could go to Canada or Russia, it's actually owned by the state, the country where it landed. They own it for scientific research purposes. Russia owns it for economic reasons. They want to sell them. So they want to own the sale of that commodity. So it really depends, but in the United States, it's the landowner where it lands. So if you find a meteorite on their property, technically, legally, it's theirs. In 1908 in northern Russia, there was this Tunguska event. Not a lot of folks are really, there was nobody there to really witness or capture data on it until after it happened largely. Anyone who did witness it, as you can kind of see by the forest that got knocked over like toy Lincoln logs, probably didn't make it through. It's estimated to be a 30 megaton blast, which is a huge, huge monster of a blast. Likely a cometary or a super bolide similar to Chelyabinsk, but in that downward facing manner. If you remember, they had a big white shady rock on that one graphic I had earlier. That was the Tunguska event rock. It knocked in an estimated 80 million trees over. So it took them forever to get through this mess, to even get in there to see if anything made it through. It just took forever. It's such a mess. But all the trees were just knocked over everywhere, and everybody's, no crater, just a whole bunch of downed trees. So kind of an interesting effect. They're very powerful. They have a lot of energy associated to them in their large masses. Well, probably one of the more famous ones that we're aware of in the upstate New York here, and some of you may remember this, is in 1992. This is a really interesting event when it happened, not because it was dramatic or a lot of destruction, but because it had a lot of funniness to it, and it was the first one that was ever recorded. This fall was actually recorded from the time it started in Kentucky. There were video accountings of it all the way until it landed in Peekskill, New York, which is kind of cool. So it was really the first time that it was witnessed to that extent. October 9th, 1992. It's just a small squash-sized rock. You can see half of it there. It's a very interesting rock at that. It's a stone chondrite. We'll talk about the types of meteorites in a moment. Probably 12,000 grams worth of mass in total is the estimate that's been handed out. This was like the luckiest teenager in the history of teenagers, by the way. She had bought this car for $300 just a few days before this rock came through and rudely smashed up her car. But she got 50 grand for the rock and 25,000 for the car. In 1990s money, that was a lot, right? I mean, that was a lot of money. She did pretty good. I bet she got a nicer car. I'm just saying. It was a Chevy Malibu, for those of you who might be wondering. The other interesting thing is the car is still kind of a phenomena. It spent a long time at the Natural History Museum in New York City, about 20 years. It's now over in a museum, and I can't remember the name of it, in France. So it's still there being on display, and the car and the rock go everywhere together. So kind of a neat thing. The people who bought it are meteorite collectors, and this is actually something that's true. Meteorites they're rarer than diamonds at the end of the day, right? They're much rarer than diamonds. So they're usually pretty pricey, but when it interacts with humanity, that thing also usually retains a value. There's been people who've cut pieces of their homes out where the rocks have gone through or caused damage on their house, and they're able to prove it. And the collectors will show up and they will buy that interaction with humanity, because it doesn't happen that often. So kind of a neat thing. And this is the Peekskill video. This is the one that was taken from Tennessee. There were about 5 of these videos in total that you can watch. And you can see all the rocks are burning up, and interacting with the atmosphere. Most of them just burned right down to nothing, or very small chunks of rock. Just that one big mass is the one that's in front. He's going long. And so bang, she made a lot of money. So so now we kind of get into the types of meteorites, and we're just going to blow right through these really quick. There are 2 common signatures on most meteorites. The first common signature is that it contains some degree of iron. The second common signature is there's some degree of nickel. On this one here, for example, you see the rusting in the meteorite here, that's iron. And the little flakes that you see, the shiny little flakes, those are nickel. It may not be a consistent amount of material, Different stony meteorites have different consistencies, but they always have some degree of nickel and iron. This one over here has more iron than nickel. This one over here has more nickel than iron. So you get all sorts, but the rest of the material around them can be differentiating in a stony meteorite. And stonies are usually lighter weight. However, there is usually a significant enough iron in it where it'll be like a regular stone, that kind of a weight to it, right? When you bounce a stone in your hand. But it'll react to a magnet, stick to a very powerful magnet. It'll have enough iron in it to do that. So that's how you can tell and they have differing types. They have common chondrites, achondrites. There are thousands of varieties of these things that can go through, and I'll hand some around in a few minutes. Then there's the irons. And the irons, when I hand one to you, your arm's gonna go like that. It's guaranteed. They're very deceptive for they're very as dense as iron, so they're very heavy. They have a lot of unique characteristics on them. Over here, you see this little carve out, looks like a little thumbprint in it. See all these little thumbprints on them? They call them, I've never actually known if I pronounce this right, but I believe it's regmaglyphs. And they are basically what they are is they're iron meteorites, but they had some kind of stone in them when they were coming through the atmosphere, and the round stone parts melted away. And that's what those are. And you can see they can be differing sizes. They can be really prominent or really small, all depending on the material that was all smashed in and conglomerated with the iron. When you cut these things in half and you acid treat them and shine up the surface, you get these weird crystalline patterns in here, and they call them Widmanstatin patterns. And basically different types of irons have different types of Widmanstatin patterns. If they have no Widmanstatin pattern, they call them as taxite. Some of the Widmanstatin patterns are so big that you would have to have a specimen like 10 foot by 10 foot to see the actual crystalline pattern in it. And then when we get into one special type of the stone, he's called a carbonaceous chondrite. These are very interesting. They don't have the same density of iron or nickel in them, so they're a little bit unique in that regard. They pre-exist the formation of the solar system, and so they have a lot of heavy carbonaceous material in them. You see how dark everything is in here. But a lot of the times what you find in these, what make them really interesting, is you'll find traces of ammonia and other organic compounds, amino acids, not life, but the things life is made of. You know, the things that are common amongst all forms of life. You will find, you know, differing amounts of those. And the other thing that you can find are little teeny tiny pockets in them of water, right? So they may be carrying, you know, in one of these little chondrules in here, they may have a significant amount of water within the actual rock itself. We don't find a lot of these because if they hit up like in upstate New York, these things dissolve in water. So they're that kind of a loose, like you can crush them with your fingers type of material, right? They're not like your hard stony rocks that you usually think of. I'll see if I can dig one out of my box here to pass around, but these are really intriguing. And then you get into the pretty ones, the pallasites. Pallasites, basically they have an olivine-like substance in them in between the iron, right? And there's nickel as well as always. But this is iron. One of the downsides to these pallasites, you'll see it in this one, they'll rust away, which is, the iron's usually very unstable because the crystalline structures aren't real strong. And so as you let these sit around like in our environment where it's really humid, they'll actually rust away over time, and you kind of see one doing that here. Some of these down here also have a similar type of compound, or you know, this one has what looks to be a very stable iron material in it, nickel iron material. So not all, but a lot of them do deteriorate very quickly. And then you have mesosidrates, which are very similar in concept, just a lot more nickel iron than there is other materials in them. So they get really pretty though, because the nickel's really prominent. It sticks right out there and shines. You sometimes even have like a weird little sheen to them. And I know I have one of those in the box as well. So that's the presentation, just to kind of introduce you to the types of meteorites that are out there, what some of the sources are, etc. Does anybody have any questions? Which one is it? This one? Oh,
Oh, one in the back here, pardon me.
you wouldn't.
You said that they dissolve in water, so where do they find most of the
They
carbon?
don't. I mean, you have to find them pretty fresh. The most common place to go hunting for and to discover those, deserts.
Yeah, that was my guess, right?
Yeah. Oh, and also the poles, where the water's all frozen. So the poles are actually really good. Antarctica is a very popular but expensive meteorite hunting trip. You'll get more. You'll find more than you can carry for sure. That's a good question, though. Yeah.
Hold on a second, so people on the live stream can hear.
Do you typically store like the pallasites in like some sort of anoxic container to keep it from oxidizing like that?
People try these, but if you look, this one's starting to fail. Even encased in, you see the little fringes of it are starting to rust. It's not necessarily just the moisture, it's the stability of the iron compound. And if there's anything when they encase this, right, you can try a lot of games, and a lot of people tried a lot of things, and sometimes it works, and sometimes they get lucky, and other times not so much. So, like, great question.
All right, any other questions?
Okay, we'll get to the show then.
All right, show and tell.
So this is, and I mentioned it, an ataxite. And the ataxite, basically the idea is it's an iron. It has no Widmanstatin crystalline structure to it. The black is rust. That's going to happen to this rock. There's nothing I can do to prevent it. As soon as they sliced it and realized it was an ataxite, it's headed for that demise. So, but it's kind of still interesting to see the material. I want you to keep in your mind, as this passes around the room, I want you to keep in your mind for when I pass one around with a Widmanstatin structure to it. Dun, 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 dun. Here are some stony, I'm sorry, these are actually iron. They're not stony meteorites. You can feel the density in the box for just two small rocks. But you can see those look like they're rusting, but they're not. That was where they were found. That was the color of the sediment where they were found. So those are kind of interesting in that way. And then we'll let you pass that one around, but you can hold it up to the light and you can see through the olivine structures, which is kind of cool. Who here knows what peridot is? Yep, exactly. Very similar substance. At one point, there was actually there were some meteorite guys who were trying to figure out how to facet the gemstones into peridot-like stuff because the structure behaves so much like peridot. They had some luck, but nobody really wanted to spend it. I mean, these things are more rare than diamonds, and everybody's like, nah, I'm good. They didn't want to buy it. So here's a couple fragments from Chelyabinsk. I did not buy this. This was sent to me from a friend in Russia. I thought it was kind of fun. They also included a piece of glass. So that you saw all of the windows were breaking. They included a piece of glass just for me. So this one, as I pass it around, this one has a Widmanstatin pattern to it over here on this side. This over here is a Sicodiolin, and the basic idea behind this meteorite is these were found in Russia embedded in trees, which is kind of interesting. So they have very wild shapes to them. Now, what's really neat about these is, I mentioned one, you need a 6x6 block in order to see any lines in the Widmanstatin pattern on this one. And it's extremely stable. I could store this in water and it would not rust. And you can see now, pay attention to that ataxite, and notice how the Widmanstatin pattern is much shinier. And that's all kind of more natural shine to it, or sheen to it. All right. And yeah, that's a Campo. So Campo de Sio meteorites, back when I first started collecting, these things were a dime a dozen. And I think it was, I can't remember, I think it's Argentina is where they were found. They're really interesting rocks. They're kind of fun. They got the nice thumbprints. We talked about the regmaglyphs, I'm sorry. And they got the nice thumbprints on them. What else is also kind of interesting, you'll see there's a little bit of rusting here, but it's always been that way. So I'm not quite sure how to explain that or what the reasoning for that is, but it's always been that. You can no longer buy these. The country of origin banned the sale of these, and they're kind of hoarding them all for themselves, I guess. I don't know what they're thinking. Now, careful. Told you. What's this guy? So this is an example of a stony meteorite, and it's a slice of one. The idea behind it is you'll see a whole bunch of these little chondrules in here, and what they are, you can kind of think of these as 3D little artifacts in there when you have a whole slice, right? So they're like these little blobs of material, and when you slice them, you can kind of see the 2D profile of one of them, or of them. That's the way these rocks all form. A lot of people will ask, is it an earth rock or a space rock, right? And when you do earth rocks, they're almost always layered, or they're blobbed together like all these random weird little shapes. So you can really tell easily an earth rock against a meteorite for that reason. So a lot of people say, is this a meteorite? And you can look at it and go, no, it's not. So it becomes a telltale sign of them. Also notice on the big heavy iron meteorite that's going around, you'll notice the surface is extremely smooth. If you look at an earth-based rock, there's always these little pinholes in them. We've all noticed them before. And what those pinholes are is air when it's lava, or whatever its state is when it's liquidish, the air module bubbles go up through and they create little channels, and that's what causes those little pinholes. That doesn't happen in space rocks. So you'll notice that all the meteorites, none of them have that feature to them. Here's another one. When this one comes around, it's also a stony meteorite. This is a stony iron, actually. It's got some mass to it. But I want you to sheen it in the light so you can see the nickel flakes that are in it. This guy. I already sent one of those around. Is this my... Yeah. He's getting rusty on the backside. Let's see. Yeah. So as we saw when iron meteorite, or as we saw with those bolides, when they go, there's an explosion and there's fragments created. When that happens with an iron meteorite, it can be quite impressive, right? This is a fragment of, you'll see how it just looks like it's been torn off something. This is a fragment of an iron meteorite that was probably much, much larger than this. You can feel the density of it. You can see on the backside it's rusting. But you can see all the jagged edges and things like that are on the end. So that's what you can identify, and you know that was a fragment that broke off a main mass. That's not the one. Where is it? Let's just see it. Okay. Well, we got the metal detector out there, right, Drew? Sometimes these were like gold to primitive cultures, because if you got one that was shaped like this, you can tell what you could make out of that, right? So you'd hear a lot of stories about they would find these iron fragments on the surface of the earth, and they would use these for making weapons, right? And a lot of them were very tuned for that, the fragments. So here's another fragment. It's kind of cool, isn't it? I have another one at home that's about this big, and the person didn't know it. They found it in their backyard, right? And this is in Southwest California. They found it in their backyard, and they were using it for, their family was using it for a doorstop for like 80 years. And I'm like, you know, that's a meteorite, right? And they're like, no, I didn't know that. and it was a big one too. I mean, it was a really good sized one. So that gets kind of fun when you find those. I have one that I bought that's a slice, and there was a tribe that had used it as an anvil. And so they were banging on it, forming, you know, other iron artifacts. And so they're banging on it. And when you sliced it, you could see the Widmanstatten pattern warping for how they were banging on it. It's kind of really interesting. So they get really neat when humans interact with these things. They don't really know what they are. You know, it's kind of neat to know that. Now, what can we use meteorites for other than just collector pieces? You know, there's a big value that these bring with them. And so a lot of collectors, when they buy them, they will ship them off to Arizona State University, and they will, there's a NASA office there, and they will take samples off the meteorite and catalog it, categorize it, try to identify it, and store them all, and they study them for science. You know, it's, you know, jokingly, it's kind of a poor man's space program if you think about it, right? Because they're coming to you. So NASA will oftentimes sanction trips to Antarctica, like I said, because you got the white snow there. Most of these things, if you haven't noticed, they're either dark brown or dark black, right? They kind of stick out, right, when they're falling on a snow bed. Or you got a metal detector and you're going across the snow surface, you can find them very quickly, very easily. They can tell you a lot of different stories as you start capturing them, gathering them, and categorizing them all together. So there's been a lot of that kind of activity. And there's one as stable as can be. And I mean, those are not airtight, right? Those are just a way to protect them, physically protect them. And this guy has done really well. And Brenham is one of the classic ones that you always find for sale out there, but most of the Brenhams have deteriorated. And this one's been doing really well until last year. There's a little speck on the bottom. You see the rust speck on the bottom? So it's doomed. The other thing that happens to the olivine too, when the metal rusts and corrodes out of those pallasites, the olivine will fall. It actually it's putting pressure on them, holding it together. They kind of turn into dust as well. Yeah, if they didn't cut it, it would be a stone. But because they're cutting it, they're shattering it. If you look, it's shattered all over the place. When they make the slices, they shatter them, and so when the iron around it goes away, they kind of just fall apart. Sadly. All right, this one I'm not going to pass around because it's not all that impressive. This is probably the most expensive meteorite I own. It's from a Martian known meteorite called Zagami, which the neat thing about Zagami, like you probably can't find these right now. Like I probably got lucky that I even stumbled on this, and hopefully it's not fake, right? Because the neat thing about Zagami, that's the meteorite, if you ever heard about it, where the farmer was working in the field in Northwest Africa. Everybody ever hear this story? It's like urban legend. And it came by and it hit his dog, killed his dog. It didn't kill his dog. It did hit near him, but it did not kill his dog. So this is a piece of that Zagami meteorite. It's kind of funny. They go around and they just chip little pieces off it and sell it for way too much money. All right, here's the mesosiderite. This is the last meteorite type that I did not pass around yet. And we talked about the mesosiderites and how pretty they are, and this is one of them. This is from a Simchan. It's a really beautiful stone when it's cut. Very stable, lots of nickel, lots of iron, lots of stone, all in equal measures. It's kind of neat. A lot of times when they facet meteorite jewelry, they like to choose the mesosideриtes for that because they're extremely shiny when they're etched surfaces. And they just look really pretty.
So, Patrick, I have a question. Like, so when a meteor shows up and NASA or somebody, takes the slices of them, what happens to the meteorite dust? I'm sure it's not just a clean cut.
Yeah.
Is that dust useful or?
Probably not. I mean, I'm sure the NASA guys, when they probably keep the dust and the sample they took off the rock, right? Basically what NASA does is they'll just cut a little window into it. They won't like take half the rock, or they'll cut a little window, or they'll cut a wedge-shaped slice into it, right? And take that and keep that for sampling. But they probably do keep the dust, but the collectors and the dealers who are making the slices, probably not. Swept into the garbage can. Thank you for your travel to Earth. Oh, there it is. So somebody was asking about things in the desert can also fall apart. These are from Imlac, which is down in 55-year-old brain moment. It's a crater down in South America, in Chile, where it's basically where all the telescopes are, in Atacama Desert. Thank you. Good brain cell. And the Atacama Desert, basically, these Imlacs were there for a long time. You can find very small skeletal pieces. They literally look like skeleton bones. Were this, right? And basically the idea is that even those rocks were doomed. Those iron meteorites were doomed when they landed. Is the basic gist of it. And so you can feel this has some density to it when you shake it, but this is basically meteorite dust. They call it, oddly enough, it doesn't apply to us. It confuses us. They call it shale. I don't know why they call it shale, but they call it shale. It has nothing to do with shale up here in the Northeast. So, but yeah, it's kind of interesting. And if you shake it, you can feel the density in it, right? Which is kind of neat. All right, this will be my last guy. He's not really. Yeah, that one's not all that exciting. Where's my last guy here? Ah, excellent. A piece of Imlac to go with the vial. Yeah. Yes. You can see it looks like a finger. It looks like a finger skeleton, the bones of a finger. It's kind of interesting. After everybody's been seeing them and everything, any questions? I don't know how we're doing on time. I'm right at time. Okay.
If anybody wants to order dinner from Sub Factory, Marianne, take them over. She'll go down and pick stuff up and bring it back. We also sell stove.
You're the last guy, Art. These two gotta get rewrapped. These guys go here. I'll be back. Yeah, the Campo. Yeah, that's a good one. Looks like Pac-Man.
So you see what's coming up.
You guys are. You must talk to the ISS or something like that. Oh, should I stand back?
All right, I guess we are ready. Well, welcome back. We're continuing with AstroFest 2025. Our next talk is actually be about this fairly new phenomenon that has sort of popped up, I'd say, in the last 4 or 5 years, maybe.
Yeah,
Maybe.
probably. Yeah,
And
probably years, yeah.
called Electronically Assisted Astronomy.
Excuse me.
Ooh.
Oh, sorry.
Yeah.
I didn't realize that.
Yeah, the mic works.
Excuse me, the mic works. Excuse me, I'm sorry about that.
And what's really extraordinary is they really aren't overly expensive, and yet the images that they create are really for what you're paying for. You know, for what it costs you. The images that you can generate out of these is really extraordinary.
Okay.
And we found even on Friday nights here that the public really enjoys watching these pictures being taken. And what's nice is, you know, they get to take them home with them. And so Dr. Keith Workman, another member of the Kopernik Astronomical Society, is going to talk about EAA, his work with that, and maybe even where it's going. So over to you, Keith.
Learning to cough by covering the mic. Sorry about that, folks. Have asthma. Anyhow, oh, so how do I advance? Just one click on a mouse? Or do I use this guy? That's fine. Yeah. Oh, I must push that one. Yep. Oh, that's better than last year. Cool. Okay, follow Patrick. I know it's tough to follow, but I got some of your pictures in here too, so I'm gonna harass you again. So yes, I'm going to talk about EAA. Like Drew said, it kind of popped up 4 or 5 years ago, and most of our members in the club, like look at Patrick and where's Rick and Marianne? They stepped out, but and Dave. These are gentlemen and folks who've really like taking pictures because you know the heavens are really enthralling to look at, and they've actually invested time and money to have, I would say, professional level rigs. They take quite good pictures. This is actually your baby steps getting into astrophotography. But I see young people out there, and you know, if you tell your dad, I don't want a telescope, spend another $100 more and get me one of these, and that way you can put it out there, and all year long, and take pictures of all the heavens. It's great. It's very impressive. So that's my recommendation. So moving on, it worked. So EAA, it's basically a way of, oh, I guess I'll read right here. It's a way of taking pictures or attaching a digital camera to your eyepiece and taking pictures. And what's nice is I saw a gentleman from the Syracuse Astronomical Society come down a couple years ago, about 5 years ago. He had a Raza, a big one, and he said, watch this. And I saw the screen, and in seconds, the image kept growing better and better and better. I said, how are you doing that? He said, well, I'm taking snapshots. Another snapshot, a couple seconds apart, and merge them together, called stacking, and all of a sudden the image starts growing. Very impressive. So with that process, show them right here, the signal rises, and the noise kind of falls off, so you have a better picture. So that's what it's all about. These devices are great for outreach. This is part of I hacked my old talk together. But we have a bunch of vendors out there. Vanos, which is one of the original ones from France. It's Stellina and the Vespera 2. We actually have a gentleman, Bob G in our club. His last name. He actually has the Vespera. He spent probably 3 or 4 times more, but then his pictures look a little bit better, not bad. But you'll see with the price ranges, it can start as low as $350, $400, up to about $4,000, even higher. And when you get in the $5,000 range, you might want to just actually buy a real rig, which has more interchangeable, more functionality. But so Vanos, if Unistel is very popular, the EV Scope and their Odyssey, that's their newest one. And a lot of these things are just devices which take pictures of the sky. And the pro version of the Unistellars actually have an eyepiece. So when you look in there, you actually have a little TV screen, and you see what you're imaging, and it looks pretty impressive. So it gets that visceral feeling, but actually looking at the stars. One of the beginner ones, which I started with, was the Dwarf Labs. A bunch of Korean grad students started doing this, and shocked the rest of the industry, and the industry jumped on a bandwagon and started making these devices for consumers to buy. So the Dwarf 2 was a nice little device. I'll talk about it, and Dwarf 3 is the newest one. The other popular one we use around here is called the ZWO seestar. ZWO is a Chinese company. They make, you guys probably say some of the better components, right? Better cameras and better mounts and optical tubes or trackers or whatever, and actually integration boxes with Wi-Fi and stuff. But they then jumped into the one to the market, and I think the most popular device now, the seestar 50, and there's something called the seestar 30, which is a cheaper device by about $150. Very entry level for families and stuff. And then now, of course, everyone's upgrading, so they make something called the seestar 30 Pro, which is going to come out in next year. They delayed it further now, maybe January. And there's also rumors there might be a seestar 50 Pro and a seestar 80. We heard at our Black Forest Star Party 2 weekends ago. We were at Cherry Springs, and the vendors were there. Anyhow, so bigger, badder stuff's coming, hopefully holding the price down low. What am I all talking about? Well, you got telescopes for visual, and you'll see some tonight. You'll be able to look through some telescopes also in our observatory domes. And then there's ones that are imaging. They look like the visual ones that have cameras slapped on the back end. The bottom line is, if you go crazy, I know Patrick had an initial monster like this built in his den way back when, and maybe his observatory. You actually see the actual optical tube. You see on top a little guide scope, a little camera. You see the big camera hanging off the back of the main tube. You see a nice big mount there with counterweights. You see a nice big tripod, and all that wiring to hook it all together. Yeah, it's an effort, but you get what you pay for, so to speak, as you level up to bigger, better equipment. But it can be a challenge. A lot of people don't want to spend the time and effort and money to do that. So therefore, they jump back to smaller things. And you have these ecosystems, like we're talking about ZWO. They make both the mounts and the scopes and the cameras and focusers. And so there's all these kind of components. So you kind of stay within one ecosystem, and things kind of work better together, the vertical integration. With that concept, I'm sorry. So what does it include? Well, it includes a telescope, focus reducers, motorized mounts to track the sky. You have the actual camera I mentioned. You have computer software then to take the snapshots and integrate the pictures together, stack them and stuff. Like I said, there's focusing devices, automatic focusing devices you have. So there's all these sorts of things. And also you have software, like deep sky software, to show you what the sky is and what objects you want to go for. So these are all pieces that you would use in an automated system. Cameras, we're talking about two types of cameras. CCD cameras, like we have in our big scopes out here, they're black and white. You put color filters in between them to get bigger, better pictures. But nowadays, these EAA devices, and I guess it's true, even your high-end cameras are one-shot color, also CMOS, aren't they? So CMOS has gotten better. This is what you have in your phone, right? To take pictures with, and they're gotten better and better. And these chips tend to be from Sony, I guess. They get better and better. They have some are meant the ones that are in the seestar 50 are really meant for, not really for astrophotography. They're kind of low light, but not the best. The ones in the more professional devices are made for low light and work much better. They have bigger wells to absorb the photons, so you have more differentiation in intensities, better images. Anyhow, what can you do with classical imaging? Well, you can do stuff like this. That's our current comet that's out there that you're going to see up near, I guess, the Big Dipper. This one's called C225A6 Lemon. One of our buddies from that we know, we see at Cherry Springs, his name is Steve Baleva. I've met him, and Art knows him. And he's actually, he was up at Brookhaven National Labs up on Long Island. And but he's down in Virginia now, but he went to Cherry Springs and took one of these shots, and I guess we missed them, but, or maybe, I'm sorry, he's Virginia now, so someone was Parks in Virginia took the shot. So this is what you hope you can see coming up naked eye. Well, see if it gets big enough, but these are one of the objects, comets we can look for. And the seestar, these little electronic devices, they have a database update, so I can go out to the web, grab more data, and all of a sudden this object will be in there, and I can say, hey, let's look for this thing in a couple of days or weeks from now, and it's a little higher in the sky, so very impressive. But with the high-end systems, you get nice sharp images like this in post-processing. With the little devices, they take a picture, but not quite as good, but at least it's like a snapshot. So that's why I'm saying these EAA devices are more like snapshot kind of things in the heavens, but still impressive for outreach. Another example here, we see this is a high-end camera, an ASI 533 blah blah Pro, and you can see this is this is the Veil Nebula, and you see the eastern and western veils and Pickering's triangle in the middle there. What a seestar can pick up is something like this, which is actually a smaller piece of the bigger picture, and you can play games. The seestar nowadays has built-in software on it, which can actually enhance the picture, so you can kind of take shots, and not bad. It's good to show people, and some of these are actual, not mistaken, these are real colors, and then you can further enhance them on the device. So, and this device I'm talking about, seestar, is in the lower corner here. That's a little black thing. It's a little lightweight kind of device you can sort of carry around fairly easily. And that's the other thing. These EAA devices tend to be lightweight, easy to put up and set up, versus the full rigs, which you saw, which has all the wires and stuff, and sometimes a little more challenging to set up. Another example. Oh, here you go, Patrick. This is your. I was taking shots at Cherry Springs 2 weeks ago, and Patrick walked over on a cloudy Saturday night, of all things, right? And then you have a 10-inch tablet, and he shows me this image. I'm thinking, well, that's much bigger than what I'm taking. It looks more detailed. So how long did you image that for? Oh, that's only a 5-minute snapshot. Oh, okay. and look at that. Look at the detail, right? And so where does the seestar fit into this? Well, with luck, seestar is a much smaller picture, and when you max it out for what's called a mosaic mode, 2x mode, I only got a small, well, yeah, I'll show you. A small, that's the difference. So that's what I was seeing initially, our little EA device. Okay, but I'm missing like all this other stuff. So you can actually max it out and say, well, I can make it 2 times the size. And it's something called mosaic mode, right? It searches around the sky. And it takes, it said 83 minutes. Well, it took about 2.5 hours, so I actually did the whole thing. But Patrick, you can see the white box is where we are. See how big a bigger sensor is on any of these bigger cameras, so to speak. And so my thought is, when you take a picture like that, and you take multiple of those, you have much more data, right? And you have more stuff to choose from. Like I might want to play with this size, or zoom in and play with this size, right? Because you have this bigger wealth of data to play with. And then you were imaging, you were taking a bunch of 5 minutes. So you took like, what, 10 of them or something like that night? Even through not so good conditions. The night before it was fantastic, so it was even better. Yeah. Well, even though I struggled under streetlights from 2 to 4 in the morning 2 nights ago, just to get that. And then I kind of tweaked it and colored it a bit. So, and just to show, well, this is the Heart Nebula, and it's the same sort of thing. And I was gonna make, there's actually a video under here. I don't know if I'll go back and show it, but it shows, well, maybe let's see if this is a tech thing. Can I pop up one more window? Will it show a YouTube video? It will. Oh. It's not showing up. It's okay. It's okay. We're not going to do that. Bottom line is they're showing how small the seestar's view was, and I said, well, and they zoomed out to an image this size. Said, well, the seestar with this new expanded mode can actually do the same sort of thing. So I was going to kind of show it off. Anyhow, we've had people, like I said, Nico from Nebula Photos said, hey, can I try to match some of these devices? And this one on the right here is the Vespera original, I guess. Also, your 50 millimeter. These soaps tend to have small apertures, but 50 millimeters is not bad. And the bottom line is he went between his rig and the EAA device, which is cheaper, and pretty close. He did some post-processing and PixInsight. Now, is that what this seestar, which we're kind of promoting, or we have it here at Kopernik? Well, the Vespera is a little bit better, has a little better chip in it. But the bottom line is it's kind of close. And then we had another guy, it's another YouTuber, his name is the Lazy Geek Cuive, I guess, from France. He's a French gentleman in light-polluted Hong Kong. He shoots from his roof. And even he tried to build a similar device, and the best he could do was this device for about $1,000. And these devices that we're using are only like $400 to $500, and less wires, less things go wrong. But bottom line is, these telescopes, EA devices are robotic. They're simple to use and set up. They're all in one. They have all the stuff you need in them. They've got a mobile app usually for both Android and iOS. They kind of know where they are by using plate solving. They take a picture of the sky and they have a database and they match it and they say, I know where I am. No GPS needed. It's awesome. And then you take those images and they stack them, and then you can do some basic image processing in the back end, or sometimes you can even offload the data and go crazy with bigger, badder software, like PixInsight, for instance. They save things to your phone in a simple image, like a JPEG. You can see it right away. On the back end, they'll save either TIFF or sometimes even FITS files. FITS are, I guess, that's the official stuff, right, Ryan? Or I called you my son. Yeah, there you go. I should pick on Dave too. He's right behind you. He did the same thing, and so those are the files. Then they have enough data, so you can actually use the high-end programs to actually do your various imaging, stretching, and that crazy stuff. These little devices are nice for the standard images up there, like the moon and stuff. But planets, they're really tiny. They just don't show up very well. They have digital zooms like 4x now, so you can sort of see maybe Saturn, but it's kind of blurry, and Jupiter maybe, and if you post-process it. But it's really meant for the standard bigger images, like the size of the moon, or globular clusters, or nice nebulas, as I said. And the ZWO seestar did pick the right size. The 50s picked the right size for most images, and now since you can go mosaic and make it bigger, you can get some of the bigger images too, like you saw like the Heart Nebula before. So they're simple and they're lightweight. The bigger rigs, much more versatile, but heavier, more wires, things can pop out and stuff like that. But then they're usually made of better quality components. So when you get when you go up to the next size, the full rig, you can swap out your optical tube, swap out your mount, you can swap out the camera, different things you want to do. But then, of course, that's cost. But then again, you've been absorbed into into the Borg. You're now into the astrophotography realm. So, but hey, they're good for simple objects. Like I said, nice showcase objects. The bad is they don't work for small targets, not modular. And will the companies last? Well, turns out these companies have lasted, the major three, or four actually. Like I said before, we had the Dwarf, that's Dwarf Labs. And I bought a Dwarf 2 for nice, easy backpack, used for scouting and stuff. Dwarf 3, that's bigger and badder. seestar came out. Dwarf 2 came out and the seestar 50 came out. And it said, we're going to counter with the Dwarf 3, better technology, but we're still a smaller 30 millimeter lens versus a 50 millimeter. And so how did ZWO do? Well, they came out with these, the S30, the 30 millimeter version to counter that guy. And they have similar sorts of qualities and features. And nowadays, since it's been a few years, they all have about the same sort of software features. They all have some sort of back-end processing the image. They all kind of will track well. They all kind of will do like mosaics. So everything is finally caught up. So it's interesting now. And the higher-end ones, like I said, Bob G, he's got the Aspera 2. You see the price goes up. That's also a 50 millimeter, but it's got a little better chip. So his pictures sometimes look a little sharper, right? A little higher resolution. The other competitors down here are your Unistellars and stuff like that. They have DV Scope 2, and now they're EV Scope. What's the Odyssey? And the Odyssey is nice and smaller, but the price range is still over $2,000. Is that much better than the $500 device? Maybe a little bit, but is it worth? All depends on your price range, what you want to do. But so it's nice. There's a variety of things you can choose from, and they are getting better. And I guess, well, they should be getting cheaper, but we use extra taxes these days with imports, so the price was up to $50. But and then it turns out to further compete, our buddies from ZWO are going to now make the S30 Pro. So instead of having, I have a thing out there somewhere. You don't need to see that. It's a boring slide. Here we go. That's what you get with the That's what you get the Dwarf Labs product, and you get a little carrying case and stuff. And you talk about the chip. It's a better chip than the original chip. I think, I'm not sure if that's 4K or not. Some of these tend to be like a 2K image. And the comparison is over here. What does it say? I forgot. Well, either way, it's gotten better. and with this device, by the way, there's both nighttime use and also daytime use. So you can take pictures of terrestrial objects and birds. As a matter of fact, that's tracking algorithms that are supposedly AI-based. And it can follow birds and stuff. They take movies and stuff. So people who do bird watching, they get these things. And at nighttime, they can sit out and take pictures of stars, too. Kind of neat. So that's the latest and greatest. I said the original seestar 50 here does just nighttime, really. The newer one, so that's basically $500 nowadays. This is like $350, maybe $400. Tariff prices, sorry. And that's the 30 millimeter versus the 50 millimeter. And as you see, it actually has two lenses. So it has a wide angle lens, so it does daytime stuff as well now, just like the Dwarf product did. And then they're going to further enhance that sucker to be even better chips. So these are basically 2K chips and stuff. It just talks about the difference between the white one and the black one. The black one's bigger, heavier. Light one's smaller and cuter, I guess. I don't know. They're all like 1K kind of, 1 or 2K kind of chips, or I should say 2 megapixels. The other one's going to be like 4 megapixels, actually, a 4K, bigger resolution. Matter of fact, this is I snapped this off a guy's video. I said this is the difference between the two, the S30 and the S30 Pro, which is coming sometime in January. We'll see. And then you can see the chip size. They actually are bigger, and it says right here, the original one's 2K, the new one's going to be 4K, and it's have a larger, wider field of view, so you can take even more pictures of the heavens, and then you can zoom in on what piece you want to pull out to further enhance or something like that. So things are getting bigger, better, and hopefully reasonable price. Then, of course, just like when consumer electronics come out, phones and stuff, Apple kind of comes in last, and they get the best, the cream of the crop. Well, Celestron, famous, I guess you will, telescope manufacturer, finally jumped into the field, and they did this last year. And theirs is much more expensive, but then they have a bigger 6-inch tube, and it's longer, and they use some of the original components they use for other telescopes, the tripods and their mounts and stuff. But they have this RASA, which stands for good for imaging. It's a faster telescope, it's f2. And the camera, instead of going back, go right in front here. So light goes down, hits the back mirror, comes up to the front. Where the corrector plate is, you slap your camera in there, and so it images much faster. So on a seestar, which I had a small 50 millimeter, this is a 152. This is 6-inch, right? So it's bigger. And so instead of me hunking away for 12 minutes, they did it in like 2 minutes. And so they have but then, as you point out, their camera's kind of off the shelf, not so good to start with. So eventually, maybe for more money, they'll put a better camera, replaceable. So that's kind of a nice thing. When you buy the seestar, it's all built in. It's kind of like a disposable unit, but it's not too bad. These guys are made for more expandability, but then again, you start with a price, and it goes up from there. And unfortunately, when you buy this one, then you have to buy filters for it. Your narrowband filters. With the seestar, they're all included. So a lot of stuff's included in these smaller packages, which is amazing. These other ones, you have to buy add-on pieces, the next drop another $500-600 here, and I don't know. So the price can get away from you. But, you get a better picture. Okay, I'm rambling about the seestar 50. Here it is. Some specs on it. It's an older chip, the Sony 462. The newer one is going to be the 585 or something like that. So it's going to be a bigger 4K chip, better resolution, better light, made really for astrophotography for low light situations. This was like a camera or chip used in like video cameras or something like that for security, and they said, well, we'll throw it in there, it's cheap. And it worked pretty well. You'll see some of the pictures we have. Features. What do these little things do? Well, if I throw a slide, okay. They're fully automated, right? It's a 250 millimeter focal length, so it's not bad. It kind of frames things pretty well, most of your objects you want to look at. You link to it initially from your phone or a tablet, and it goes by Bluetooth, and it goes to Wi-Fi. Has built-in sensors as a compass, like a magnetic compass. It has the filters built in, so you can take a normal shot of some bright object, a big fuzzy lump of stars we call as globular clusters. Well, hopefully they come more pinpoint. Or you can take nebulas, and you kind of put these filters in, which are called dual band filters. So it has oxygen 3 and hydrogen alpha on the spectral line, so it eliminates all the other light. So even in the light polluted skies, like tonight, we'll show it off. We did it last night too. The moon's up. We're taking pictures of stuff, and it's like, wow, that's pretty cool. Well, we had the filter in, so we kind of blocked out a lot of it. Pardon? Oh, yeah, well, I'm getting there. Yes, it does its nighttime stuff, but it comes with a full solar filter, and we looked at the moon last night too. So it does automatic autofocus. It's automatic go-to. It's alt-as, it tracks. It's got a built-in database of the sky, if you will, sky map. You can actually go on a map and say, I want to take this object there, and it'll go over there and zoom in on it. It enhances the image. It does stacking. That's what all these devices do. So it takes a picture, usually 10 seconds, and then maybe another 10-second one, another 10-second, and it kind of sticks them together. I guess as you stack them, the image quality, the signal goes up, and all the weird things kind of fall off. So you get better. So you have this image that grows in front of you and say, that's pretty cool. Every 10 seconds. It goes from 10 to 30 seconds. It turns out there's another mode you can put the scope in up to 60 seconds, as long as it's tracking well in a equatorial mount. We'll talk about that. So, and it saves the files off for further processing on the back end. And so it's all this stuff you have to buy separately, included in one little package, which is really kind of neat. So you got almost the professional kind of basic tools and something you stick out there in a tripod. You go on your phone and say, set up, take pictures, and you walk away. It takes pictures. And the cool thing is there's something called station mode. So instead of being point to point, you can be on the Wi-Fi station. So I set them out there in the field. We link the seestar to the Kopernik's Wi-Fi. I put my phone on Kopernik's Wi-Fi. I'm walking around a building. I can watch what's doing stuff. And I can search the internet on your phone at the same time. So and the other night I ran out of space on the device. And I'm imaging like, but it's taking 60 seconds. So I had some time. So I actually linked to my Windows PC. I said / seestar. All of a sudden the directory popped up. So it's taking pictures, saving stuff to its internal memory, and I'm also Wi-Fi connected to it, pulling data off of it to my PC so I can offload stuff, so I have more storage space so I can store more pictures. That's one of the bad things. The initial seestar is only 64 gigabytes. The newer ones will be 256, so a lot more space. But you can many imaging runs many nights before you start filling up. Anyhow, I'm rambling. So I take pictures in really dark skies. See the really dark skies right there? I'm getting sun. I put suntan lotion on. That's our front lawn. And Patrick understands. He's next door. But with my phone, this picture got enhanced, of course. But it's pretty bright. But Jenny back here made a dew shield for us. And then I found another one which actually pops off. So I use either one back and forth interchangeable. But that does help keep the light off the initial lens. And I looked a little bit the other way overhead, and it works quite well. This middle shot here is a picture of us at Sherry Springs last year when the sun was coming. I said, I got to take a picture of this. Looks cool. And you can get shots, like this. Like I said, the Western Veil Nebula and stuff like that. And that's when you're in really dark skies, it comes up much faster and quicker. That's a 31 minutes shot. Just a little background of the app. Where's the clock here? My sort of one time? Yeah, I'll keep chugging along. It has, like I said, it has the new screen. It's an updated. You got something called stargazing. So you look at the stars, has the nebulas and galaxies and stuff. One called solar system, which basically is all your planets. Has scenery, so I guess it's focused on one high, like telephoto lens. So I guess you could take pictures. I've never had interest, but I guess you can do that. You can look at your album, what your picture you've taken, then you can like share them out on social media or to your local device. It's got something called, deep sky stack. So it stacks it when you take the picture while it's taking it. But then after the fact, you say, I want a darn satellite went through or a plane, and I have to go back in those images and I can delete that one slide out, and let's stack the rest now so look at a better picture. So you can restack. That's kind of nice. It's all on the device, so I haven't taken anything off, all on your phone. And then it has something called Plan. That's new. You can actually plan your night. I want to look at 3 objects. You pick up from the database, and you have a timeline and stuff, and it shows where they're on elevation. And you set it up, and then you go to bed. In the morning, you got all this data on your device. How easy is that? So when you first turn the scope on, you go in advanced mode, and it says, level me off. So you have to level it, and it has these like 2 little dots like that. And eventually, you level the scope, and it says, hey, I'm happy, and it turns green. So you know when it's nice and level. So that's basically the setup. Not hard. And then you go back, and you start taking pictures. And it'll even suggest, hey, these are tonight's best. M42, that's Orion. And Orion, that's the sword of Orion down there, if you will. You have M31, Andromeda, the Crab, the Dumbbell, M27. And it says, planets, what's up, and then you can pick your galaxies, nebulas, or clusters. These are deep sky things. Or you can go, like last night, we did the moon. And I gotta say, we had 3 seestars out last night. Dave, mine, I talk about Dave, mine, and I guess Kopernik's, I think. And you can't get the moon. I'm like, it's right there. And until Patrick pulled me aside and said, Keith, well, let me teach you something. The sun was up. This device looks at stars, plate solves, and knows where it is. It wasn't dark enough yet. And so we're trying to find the moon. Couldn't find it. So the best it is, we kind of put it there. I swear we put it on yours. And I went over here and said, I'm going to start searching for it. Like, son of a gun. And so we went manual mode. And get over there. And when I got close, and so, okay. And then you hit another button that says, track target. It gets a target, centers it, and tracks it. Whew, then you're good to go. But yeah, it was too bright, and we couldn't, it had no frame of reference, so to speak. And so it was kind of funny. And I couldn't figure out, why the heck? The stars really well. Anyhow. And same with the sun gets close like that, solar filter, and it plays games. Once it sees it, then it can kind of find it and lock onto it. But, so a little extra work, but that's not much work for what you can do. And then when you pick your object like the Andromeda, I guess at 31, here it shows a picture, shows where it is during the evening, and right now at this time it's rising, it's going to get higher. So if I image from here to here, I know it's going to be overhead, not in trees. So you can kind of plan for this stuff, and it's all included, which is quite nice. I have no idea why that's there. Oh, that's when it's initializing. In little tiny letters, it says horizontal calibration does that, and it does preparing for enhancing. And it's, can I go back? I can. It's got a little clock there. Turns out that's one of the things we do when we do astrophotography. It shuts off the lens and takes a picture of darkness. Well, it's actually looking at the chip, and the chip has heat on it, heat's errors, and these extra little artifacts are on a chip. And it takes a bunch of dark pictures. So when it takes a picture of the actual thing, then it subtracts off those errors and you get a better picture. That's one of the things it does. You can also do flats for, I guess, daytime stuff. I guess that's for your dust bunnies and stuff, but you can actually do that also. I've not done it yet, but you can put like a white, like a t-shirt or something, sunlight pictures, makes a database of those too. And this is based on what I'm shooting. If I'm shooting at this time of night, this temperature, 30-second exposures, it'll make a new database. Go through a process and take a bunch of darks. So it has this database of chip errors always on the chip, and then it tracks them off the image before it stacks it and makes a nice picture. Yeah. No. Another feature of device. When these guys set up their scopes, they got to put, well, they have big battery and stuff. They have to put straps over the lenses to keep the dew off, ambient temperature, you know, and a little dewing up the lens and maybe the eyepiece. I guess you have a camera, no eyepiece, but on the objective. This has that built in. And if you flip the switch on before you start, I've owned this scope since 2023 as an early adopter. I got mine for $399. Thanks to Art and other people talked about it. I could get one of those, right? And Mark, he's not here, but he has one too. He got one early and stuff. Yeah, I've never had a problem. In the wintertime it's out there. Well, maybe in wintertime it's not that bad. But all summer and stuff, and Terry Springs when it gets dewy, no effect. But then again, using those dew shields we put on for light, I put those on too, and that gives an inch or two, so that might help too to keep the, you know, from dewing up. But I've never had any dew problems. It's like, this is too easy. Sorry. So, and what it's doing, it's slowly sucking into astrophotography. Like, oh, I'm going to have to talk to these guys soon. I have to buy a camera. So anyhow, one thing is, like I said, the imagery is small, but you can do something called zoom mode, zooming and framing. This kind of, well, it shows that's your normal size. You can actually zoom out to like twice the size. So I was trying to show Patrick, well, I can get a big picture just like his picture, which I couldn't, as you saw. I can go only that big. And then bottom line is, you can actually then frame it. So if the Andromeda galaxy is at an angle like that, and that's all I can get, if you're lucky at night and it's at the right angle, you can fit it into your rectangle. You're lucky, but otherwise, darn, I can't. So you can actually take it and make this box, and then you can kind of rotate it so it fits in. And so what I didn't show is this being rotated so it fits across. And right now it's fitting all to the size of that box. You can take this red box and turn it, shrink it down, so you can just kind of just encompass just the galaxy itself. And then when you take the pictures and it starts taking them, then it starts showing you the rotation. Now this is, of course, the object change. This is now the Western Veil, which is a broom handle. But you get the idea. It starts moving around the sky, and it'll fill in your picture, but it takes many more pictures. It's called mosaic mode. So that's why it's a software update. Just like in your electronic cars, you download later, software updates, new features keep appearing. It's just over the last year, it's just been amazing. And so it'll take more time, but eventually it will fill in the whole box, and you get a bigger picture of your object, and then maybe rotate it the way you want it to be seen in a final picture. Yeah, stargazing. Oh, I was supposed to do planets, solar system. There's your solar system planets. Last night we hit the moon, and well, eventually got there. Well, you think, or planets like Saturn shows a picture, talks about, shows the height and rise. That's sort of zoomed in. It looks like Galileo saw Saturn, maybe. It doesn't look that good. But so for planets, it's not the thing. But for most deep sky objects, it really is quite impressive. I'll show some pictures later. Oh, by the way, you take pictures of the moon or planets. In this case, they're too small. The moon, you get a snapshot. And Dave, you wanted to do this last night. You said, let's take. You did take a picture. You took a movie, right? Like 2 minutes, and it didn't work, and I didn't know why. When you take the movie, you got set in something called RAW mode first, so it saves us a bunch of RAW files, the FITS files, versus a bunch of JPEGs or something like that. So you took the movie, but it was in the wrong format, and that's why it wouldn't do the post-processing. So before I came up, I said, this is why, and I'm glad you're here, so I can tell you. So when you take the image, you gotta set it right, and that says RAW there. So when you go back to your file folders on the seestar device itself, it's a file directory, it says RAW, and then you go, and up top says stack. So you click on it, you go into the movie, and then you say stack, and it will stack them. And basically, I guess like when you take planetary images, you take a movie of the planet, because it's bouncing sphere, blah, and it pulls out the best frames and throws the junk away. I guess it must, unfortunately, I think this is a device you can, like with post-processing software, you can probably set parameters, but this, you get what you get, and it's something down the middle. And it works pretty well, and then it shows, hey, stacking is seated, and they say, you know, check now, and then it'll show the picture of the actual object you took, in this case, the moon. And it comes out sometimes sharper than a snapshot, one picture. So you can do stuff like that. And I don't know if you can apply that to others. I guess you can try the other planets, but it's either Jupiter or Saturn. They're gonna, and some people have done that post-processing with Saturn or Jupiter, and you can see some of the bands. As Art pointed out, right? The guy from the back there, solar mode. They give you a solar filter, so it's a white light filter. If you're out there with their real telescopes. They have solar scopes, which have etalons and double stacks, and they're really getting awesome pictures of and even imaging that stuff. In this case, you'll get like a white light view of the sun. But actually, ironically, the filter gives you a very orangey kind of view. So when you look at the sun, it looks almost like it's cute. It's like almost made to be looking cute. No, it's orangey, right? You don't see any prominences, but you see like solar sunspots, right? And most times, those scopes you look out there, you see like a white sun with these little blobs on it. seestar said, well, we'll make a cute little. And you can also do movies there too. I did a movie. I did a stacking of a movie, so I have clouds going by, stuff like that. So I went to take a picture of the eclipse, of course, and up here in New York, and clouded out. But anyhow, oh, by the way, it also has a consumer replaceable battery. So the battery lasts about 4 to 5 hours. If it goes bad, you get two 18650s and you slap them together. You can make your own battery pack and plug it in. So that's the bottom there. Also, like I said, it's alt as, right? And so when you take a picture like that, over many, even over 10-second shots, over time, the sky does move, and your data will start moving and twisting sideways, and you see you're missing data, so it doesn't look good. People complain, we want a polar mode, an alt as mode, EQ mode, if you will, equatorial mode, and you got to point close to where you are. We're at 42. In this example, it's 46, so 45, whatever. It gets happy, and when it gets happy like that, then it says you hit the button on the bottom, and it goes and finds. So it'll say closely where you are, line on Polaris. You hit the button, and then it turns around to the ecliptic and takes 1, 2, 3 shots across the ecliptic, and uses its plate solving of the sky and says, I know where I am now. And if you're off, it'll complain. You're off by so many up and downs. So you modify your scope. You spend a few minutes, and then we get within one degree. It turns green. You get a check mark. Good to go. What's nice about equatorial mode is you can take longer pictures, and so therefore, like these pictures here, I took in equatorial mode and also mosaic mode. You don't get any sky rotation. You get the full data. You're actually tracking the image properly across the sky as Earth rotates, and so you can get some really good stuff. This one is one of my better ones. I actually went crazy, and I did a lot of time on it, and I post-processed with on the device just with some of the coloring stuff. And then here's another mosaic one where I got. Actually, this is not mine. I stole this from someone. Sorry, thinking of reference. But you can see there's M31, M32, and M110 there. You get them all in the same frame. When you have this bigger mosaic mode, we can stretch the thing out more. It also has something called AI denoising. It'll take some image noise and clean it up, make it a little sharper, stars sharper, stuff like that. You get what you get, whatever it's built in. Some people say if the noise is too much, you lose stars and the image looks fake. Oh well. But for snapshots to show people for outreach, it's fine. And then you can do things, once you get it set up like that, you can then you can play with the brightness, make the image brighter or darker. You can make more contrast, makes the stars, the sky look a little bit darker. You have color intensity and boost it up more or drop it down. And then you can kind of rotate and crop it to a 16:9 or a 1:1 or a 2:3. And then when you get a nice setup the way you want it, you can dump it out to social media, either to your device on your phone, or we have a Discord, so we post it on Discord, and you can see them. Your friends can see them. This is another one I took just this week on Wednesday. It says 33 minutes. This is a tap hole. Looks pretty good. It kind of, I mean, the fact that, when we look at our telescopes visually, we see these white fuzzies with cameras, because they're so much, like 1,000 times better in our eyes. They just pull in this detail so much nicer. Let's see. I mentioned this before. It also has a plan mode where you can put like 3 objects in a row. It shows where they're going to be in altitude in the sky. You can set them up one next to another, and then you say go, and it'll just do them. I haven't done this yet, but I'm planning on using plan mode more often. That's kind of cool. And of course, you go to the website, like I'm hawking the seestar. But they have lots of things talking about how you do video stacking. Another feature is 4K. So it does something, I think it's called drizzle, where it moves the cameras a little bit like that. So your 1K image supposedly is a little more, that does what? More for detail, I guess? Is that, it's emulating 4K? Okay. So it tries to, I guess it tries to make the picture better. Yeah, there you go. So they threw that in too. But when the new version comes out, it'll be a bigger chip, so it'll be built in. It does, like I said, it does the hot pixel correction. That's the flats, or the darks, as the flats for lights, for your dust things. Has equatorial mode. Has all these other really kind of cool modes in there, and the website has them all in its little tutorial to show you. So it's quite user friendly. And then people said, well, how do you make it even bigger, better? And I said, well, there's some add-ons. And so what we did was, sorry, Jenny, your dew shield didn't pop off nice. So I went on Etsy for $10. Oh, I'm sorry, I went up to $15 now. I bought this 3D printed thing, and this is someone got the idea that, hey, when it cuts its power at the end of the night, or before it crashes, it does a shutdown at 1% power. The arm goes back down, it goes back to sleep. This dew shield will actually pop off. That little nipple on the bottom there. It hits as it closes and just pops off nicely, so it falls on the ground next to you, so it doesn't break anything. So that's kind of neat. So that's a nice add-on people want to have. And like I said, just a dew shield in general with that and a built-in dew heater over 3 years of nuts within different conditions. In the wintertime, it's just no problems at all. Works really well. Another nice add-on I use in mine, you'll see tonight, is I bought another 3D printed battery holder. Another high expense, I know, another $15 item, 3D printed. And that slides on the side of the back of the scope, the robot telescope. This piece moves, this piece is stationary, right? And the bottom line is I used to have a battery on a table, and USB-C cables, and they'd go around and around, and all of a sudden it's tripping on itself. And when you mount to this top and you plug it into the side, it's all nice and compact. There's no cable issues. It just follows with it when it rotates around. So that's a nice thing to have. One of the other things early on we got, which Art said, I'm one of those too. We got these levelers. So when you use the standard tripod, you're in Alt-Az mode. You got to level it, so you can play games of trying to pull legs of the tripod up more, or you can get this device. And yes, you can buy it for big bucks from the big companies, or go right to China and get like 2 for the price of $10. They just have little wheels, and you just balance them. They have a level there, and you can see where you're leveled off like that. And that helps you set up a little faster. And when you're setting your level, you can go and start the imaging. Also, now equatorial mode that they came out just about 2 months ago, lets you put it on a wedge. So you have to aim your device toward, so lean over, to aim toward a North Star. So the classic one is Skywatcher. They make a nice one. I, once again, didn't go for the $90 fee. I went right to Temu or AliExpress rather, and got mine for 20 bucks. And so mine's like, it's probably the knockoff version. Someone warned me, hey, it's got a knockoff one, it might rust and stuff. But so far, I've had it for a while and no rust yet. But it does kind of work nice. But then again, as a shoe, which kind of gets in the way of the bottom of the seestar. Turns out I was watching a video early before I came up here, and so I said, hey, there's this little washer thing you put on. Gives you just enough space. You put that in the bottom of the seestar, and then the other place you zip into the bottom of the mount there. This is a different mount, by the way, but it'll be the same sort of deal. Instead of using a little shoe which slides it off, you can use this device instead. And that way it fits inside the seestar's case when you pack it up, you don't have to take things off. Oh, that's a nice little bonus. So you can buy these. So there are low expense ways to get it set up for equatorial mode so you can get longer exposure and better pictures. Back in the day, a year ago, they said, hey, you might want to get this thing called a Batinoff mask. And it's this pattern, and you kind of slap it on. It's on 3D printed disc, and slaps onto the front of the lens there. And you can actually look at it, and maybe through autofocus, it might even do that too, I'm not sure, to get a better, sharper focus. But then they updated the software, and like I said, when you go to take a picture, it finds the object, it does the autofocus. It works really well. I've never used it. I bought this, I've never used it. So I wasted $15 there. Or, I'm sorry, about $9. But you can get one of those too. People like to look at the sun. I can't find the sun. Well, you have little solar finders. People 3D printed these suckers, and you go on. It's a holder for your thing, and the sun has a pinhole, shines through it in the back, shows where the sun's showing up, so you can turn it just right to line it up. People outside that have the same sort of device with their telescopes in a solar party outside. Images, the moon. It's not bad. It's fairly sharp. Like the earlier scopes didn't have such good quality, but the seestar not too bad, and the S30 is probably just as good. Like I said, solar stuff. When I was first doing this, I had no idea where the sun was. So I took this zoomed out picture. I was like, oh, that's kind of artistically kind of interesting. Got into the trees. That was a whole accident. Here's the Pleiades, which I guess you should see nebulosity, right? All the images out there know what it looks like. I then got crazy and said, let's bump up the contrast. And I killed the image, so nebulosity went away. So you got to watch what you're doing. So for normal folks, it looks good, but for those who actually know what the images look like, they have more appreciation. So it's for the process you do the right way. So, but for snapshots, not bad. Galaxies. This is the Leo trio, right? Yeah. And 66, 65, and the Hamburger Galaxy. That's what that is. Yeah. It's NGC 6329 or 28. Looks like a hamburger, I guess. Not bad. I imaged these for 7 minutes and 21 minutes, and this is before I really had the rotational stuff in that mosaic mode. And so if they line up just right, you're lucky. And also there's a way to put things on, to go back and look at, it'll highlight what the object is and circle it for you as well. So it's a good educational thing. You can put out, you can put out there in 7 minutes and see this stuff. It's quite nice for the price. Versus a telescope you're trying with your kids and trying to, and this is the way to go, in my opinion. here's another challenge object. I think this is in Orion's belt. This is the first star, right? Next to M42, but this is the star across the belt. And you see the pony and the candle. This is called the Horsehead Nebula, right? And this is called the Flame. And not bad. I mean, it's short of stars blowing out, but I wanted to enhance these objects. So when I played games, I put more contrast on and brought up a bit coloration, because it is already kind of H-alpha, kind of reddish like that, I guess, right? But so I kind of cheated with the on-board processing and said, "Oh, I'll make it look better." Uh-oh, and I guess with that, that's it. So, so that's my presentation. So I hope you liked it. Any questions or any answers? Uh-oh. It's like, let's make a deal.
Sorry,
I'm
I'm
sorry about
managing
that.
multiple things here.
Sorry
Any
about that.
questions from the audience? I see Art's hand went up first, I think. So I'll bring
Sorry,
it back to her.
In Dave's roundtable talk this afternoon, one of the participants asked me, is it better to get a S50 now or wait for the better chip to come out? And so what's your opinion?
Yeah. Well, I'm afraid to spend the big bucks and get the full rig yet. So I'm waiting for the S30 Pro to come out, which anytime now. I mean, they showed us this device working at NEAF, the Northeast Astroforum, down in Rockland County at the, outside the city. And that was in April. Pretty good. And they said, we'll get it working this summer, in the fall. Now it's fall. Well, we go to the telescope.com or High Point Scientific. Well, now spring. Some must have supply chain issues. But I'm going to try to get the S30 Pro because that's got the bigger chip, 4K chip. And it's going to take a wider field, and it'll be smaller and lighter and move around. And I'm just going to kind of compare. And, are these disposable telescopes? Yeah, potentially. Some people, he's shaking his head, yes. That's why you buy the big rigs. You got the good stuff. Then you replace component with components, and you got more longevity. Yeah, you're laughing. What was that? The famous the Chinese gentleman who has a YouTube channel. I was going to put his thing on here. He's big into astrophotography. He said, yeah, these things are, but they'll get better. And they are getting better. But I mean, the only thing we know about officially is the S30 Pro. So I would wait for that actually in hopefully January. But Mark talked to ZW at Black Forest. The guy said, well, we might do the S70, but we might actually go to the S80. So they're thinking about a bigger aperture. And why? Because their competitors, Unistellar, has the 114 and an 85, and they're at, well, the $2,000 range and higher. But I mean, I hope these devices will come out in the $1,000 range, maybe a little more. But for beginners, they don't care. They'll use a small one. But the pros will have the better imaging stuff. And even now, when you go on these websites, people are using the S50 and the S30, and they're post-processing after many, many hours of imaging, and they're getting pretty good results. It just takes longer than the pros here who got the big cameras taking these quick shots, which have all this data, right? And I guess as you harvest more and more data, you get better and better pictures. And you know how to play the game with the professional software like PixInsight, which I've seen you can stretch things and you move the stars, enhance the backgrounds, drop the stars back in. It's like God, Unfortunately, these other ones, well, we just have serial, which is simple stuff. But there's a lot of free stuff. But I would probably wait. I don't know. I mean, if you got the money, you could go crazy. You could spend $4,000 and buy the Odyssey from Orion, or from Celestron rather. It's a big one, but that's 50 pounds now. You got to set up. It's not portable. If you want more portability, you get the smaller ones like this. And like the Selene Unistellar, they're like backpack size. They are bigger, but they're in the 20 to 30 pound range versus the 5 to 7 pound range. So it all depends, I guess, what you want. The variety's out there. But I'm personally going to wait for the S30 Pro and fantasize for the S80 Pro someday. But as I said, chips are going to get better. And I guess Sony keeps producing better chips, so I guess there'll be newer cameras. And yes, Patrick and I had a discussion last night about this. And he said, I would probably wait, because there at some point, ZWO is vertically integrated to put all their stuff together in one big package. So the camera has power in, it has, but one of the cameras that has a finder in, or what's it called, a tracker, the guide scope, right? And a bunch of other stuff involved. Maybe they'll put the Wi-Fi in or something, maybe one package. So getting bigger and better. But I mean, like I said, you saw what the S50 does. That's the old granddaddy. And the S30 is actually wider field and lighter weight. And like I said, you you can zoom in a little more. It might not be quite as sharp as the S50. Some of the people who are pros out there like the S50. And by the way, a lot of these guys who have the big rigs, you're imaging one object, you say, oh, I'm playing something else. So you spend $500 and you get the seestar and you're doing two things at once. So it's fun. And we went to Cherry Springs 2 weeks ago for the Black Forest Star Party. And in the old days, mere 5 to 10 years ago, you look down the row and there's people with their big dobs and they're visual observers. Now you look down the row, it's like, where is everybody? You see these tripods and little red lights and stuff, and it's all these robotic telescopes taking pictures. Not only the seestar, but also the real ones. And they're all in bed, so it's like, wake up. No, actually. But people do go a distance to get dark skies, to get good imagery. And by the way, I saw a table, and it is true. You saw my front lawn, nice and bright. It takes longer to get a good picture than when I'm at Cherry Springs. It's like a quarter of the time. It's like, ooh, there's more stars. Wow. So you'll see tonight if you're around here, we'll do more with the device itself and and let you play with it too, because I have a tablet. You guys can play with it, and it's quite nice. And how fast you can find stuff and do things. So I would. It all depends. I'm sad for the answer. Sorry, Dave. Sorry, you're gonna. Just trying to finish up here.
Back on one of your slides, I couldn't catch it quite fast enough. Can you remotely power on the S50?
I don't think so. No. I mean, this one gentleman with the I was just trying to go back to the plan mode. This one guy said he was with his family camping somewhere. So he set this device up in a corner, so maybe by his tent or something like that. And every morning he'd start up again. And it would sit there idle all morning until at the right time. Then it would start imaging at nighttime. So he had to restart. It seems like he had to even restart the device for each new day for the plan to run. I don't think you can stay on and run off. Well, run out of power unless you had I guess you could plug in a USB cable to it. But he sort of suggested you had to turn it on each day to resync it.
Oh, yeah.
But it's physical. There's no remote stuff, unfortunately.
Push the button.
Yeah. But then again, if you have it on and it knows 24-hour clock and it had enough power, it should just next day should just run the plan over again. But I'm not sure. I've never played with that. But it sounds like to him he had to physically do something to reset it each day. But enough people complain and we'll get a firmware update next year. That would be very cool. And some people will buy a bunch of these and set up a bunch of these and they're all imaging the same object. So instead of getting one data's worth, they get like 5 times a day, and they cheat kind of like games in the back end. That's what I've heard. But who knows? We'll see farms of these like solar panels out there taking pictures. I don't know. So any other exciting questions?
Which model did you have again, the 50 or the 30?
I have the 50 because that's what came out.
Right. And you said you've had a couple of years, right? 2023?
2023. Well,
so I'm curious, since you just mentioned the firmware updates, how often in those 2 years have you done those, and how long do they take? I mean, what's the
it's
maintenance
long and
like?
arduous, and I turn the phone on.
Yeah.
I go to the app.
Yeah.
It says, hey, update the app. Okay, I'll update the app. Good. Most times I turn it on, and it says I turn on a device, and the device, you do one point-to-point Wi-Fi first, and then because I put it on the LAN or the station mode, it's called. It goes out to the internet. It goes, oh, wait a minute, hold on there. Software updating, and it does it, and then it reboots itself, and it's like, okay, that was easy, Yeah, it's just a few minutes. Oh yeah, you've experienced the same thing, yeah, right? And Dave, yours is newer, so I don't think you've had many software updates come to your device yet, because you bought new recently, right? Yeah, you probably the latest version, yeah. And even the dwarf guys have similar sort of stuff going on. I imagine they all kind of do, but yeah, it's just like a Tesla or electric car. I've got a software update. You've got mail. So yeah, and it's stable. It's slowed down now, but I would say most of this year, every 3 weeks or so, new things are coming out. It's kind of neat. It was kind of neat. But and even now, for something better comes out, it's still quite capable. You saw the pictures you can take; it's not bad. But this guy might be a little better, and the Pro version will definitely be better, but it'll be a wider image too. So I guess like the real guys can probably then pick out chunks of your image what you want to focus on if you're taking a big swath of the sky. So yeah, it's not bad. I mean, it's quite, families like it, so. Well, it's a good stuff, yes. Oh, sorry. I forget. Run
I guess I'm just thinking, as somebody very new at doing any of the observing, and with a camera I still have to get set up, or a telescope I still have to get set up, which is old tech, not even tech really. The thing that comes to my mind is how long are you going to wait before you get started on this? I understand people who've been at it, got some equipment and so forth. Okay, you want to get something that you're going to be able to stay with for a while. But I think for a lot of us, the question, the appeal of things like the seestar is, hey, this is a whole lot easier to get into and not have to wait, so long.
turn the app
And as you indicated, you don't know how long it's going to be before you get that S80.
I'm going to say that.
Yeah,
At first, when you're an
Right.
early adopter,
And
it talks to you in
so-
Chinese. They
yeah.
make it English, but then we switch to English.
Yeah. So,
But it says finding object,
Yeah.
object centered.
yeah,
Matter of fact,
just the
can be annoying at
for the newer people.
it's made
and it
exactly
is,
for
I mean,
someone who
it's-
doesn't know. If you can use a phone and push a button, you're an expert.
Okay,
I
you
mean-
make my point.
I mean, the dwarf, which was a year earlier, dwarf 2, more, set up a tripod, you had leveling issues, and it had like weird menus on a screen while you're looking at the object. This is just, it knows. You look on the database. I'm gonna take a picture of this nebula. It says, well, I need to narrowband filters, so I'm gonna go find it. I'm gonna autofocus for you. I'm gonna take my darks, autofocus, and I'm gonna put the filters in for you, and I'll start taking pictures. Oh, I don't know how to do that. Well, you don't have to. I'm just gonna do it for you. And then you see it, and it starts growing in front of you. It's like, that's pretty darn cool. And you don't have to save the subframes or little snapshots of those images. You can just take the nice picture on your phone. Like, I'm trying to find something nice on my phone to look at. And you can dump it your phone. I'm going back for that Rosette Nebula again. There's the Pac-Man Nebula. Looks like a little Pac-Man. And you can take pictures of. There's the moon and Jupiter, the moon and Venus. Yeah, Pluto. That'd be fun. This is the 2 weeks ago. We had the sunrise, and there was like a conjunction, but slice the moon, and so I took a picture of that, and then I shot off to the side. And I got M81, M82 as the sun was coming up in the sunlight and dawn. I was like shooting images, like I can't believe I'm doing this. They didn't look as good, but it took them. I'll show you my phone. Here's like the Rosette Nebula. Like this out Cherry Springs. There's so many stars. What visually through your scope looked really neat. Imaging wise, there was just too much stars. But when you take them on different sorts of skies, it doesn't quite get as well. But really dark skies, it's works quite well. So that's why people come from all over the place, these dark sky parks.
So it just seems to
enjoy it.
me that.
But you can sit right in your front lawn like I do, and
Yeah.
like where's my dark side picture here? my lawn, I'm a wise guy. I didn't think. When we were doing visual observing, me and Patrick, we'd go out there. I put a shade over the light to block it. And unfortunately, I got 3 of these suckers. You just have one on the end, and you have it shines, of course, like the driveway. It didn't help. But so at nighttime, with my solar panels out, I get free energy, free lights, and it's pretty bright. And but you could set stuff out in pretty bright stuff. And even when it's somewhat hazy, it still sort of pulls the narrowband stuff. It still kind of penetrates through some of that haze up there. And you're still gonna. It may take a little longer, but you're still gonna picture, and you'll get some really really cool stuff will come popping out. So and galaxies and stuff. Now it won't be as good as. Like they can zoom in on galaxies and make them bigger because they have bigger imagery and they have more resolution. But for most average stuff, it's enough to really get you hooked, and you'll be enjoying it for. I'm on year 3 in this, and now I'm realizing, wow, their stuff is better. And I might want to start going over this way. And I'm sure that there'll be more integration of this stuff, so even their rigs will get simpler and simpler, and maybe less expensive. I doubt, right? Maybe. But yeah. But yeah, it'd be perfect. You'd love it.
I was wondering if it is able to have like continuous power because I did see one of them is like USB charging. I was wondering if you could operate it with it on the charger.
It has no official plug-in, but it has a USB-C port which plugs in. And I was doing that for a while, but as I kept going around the sky and stuff, the cable got kind of wound up on itself. So that's why I went back to getting that external 3D printed mount, which holds the battery pack. That one there, right? And so you put your battery in here, it sits off the back like that. There, one across the top. There's other people make it. All like people on Etsy make these things. It's cheap. It's fantastic. And I spent a lot. I went to Walmart, $8, and I got a battery pack which lasts another 4 or 5 hours. So I probably got 8 to 10 hours, all depends, of imaging. That's a night right there. If you want to make it permanent, I guess you could, but then it kind of closes down to a position, then it opens up in a position. It only goes so far. It can't go around forever.
Right.
So if you had enough cabling, you probably could make it so it wraps around just once, and it could come back, and it would probably be okay. So if you had the USB plug-in, I mean, I put it in my external battery pack, and it charges this device. This device is always charged 100% all night long. And then when it starts going down to 99%, I realize, oh, the external battery's empty. Now it's just being on its own internal power. It goes down for another 4 or 5 hours. 5 hours. They say 6 hours. Well,
I was curious because you were saying some people like to run it for like 5 days.
Well, this guy actually set it every day, and I'm sure he'll probably charge up for a new battery pack in like that. And but he had his plan, so I had the same exact plan over and over. So I'm going to collect like 90. It can't be 16 to 20 hours of stuff over like a week. His family go and they do something at the campsite, and at nighttime just doing this stuff.
So I use a Jackery battery.
Oh, there you go. Yeah. So, yeah. Yeah. Exactly. It doesn't draw much. Yeah.
Okay.
Yeah.
Thank you.
Yeah. But you can still get pretty big batteries. I get like the cheapy one from Walmart, and I get 4 hours. That's pretty nice. And yeah, with the both, and if you had the bigger ones for a higher discharge, you probably go for maybe 2-3 days, maybe still. But then it's more weight, and if you're leaning over on the equatorial wedge, tripod might want to tip. So it's almost like a counterweight in the back, kind of holds it on the back end. So it kind of works out fairly well. You can see this picture. Some have a much bigger battery. Mine's like half that size. You got a much bigger one. Right. Some. Yeah. Things get slower. Yeah.
Source you use, it's got to be able to get down to like those Jackeries go down to like 15 degrees Fahrenheit.
Yeah.
And at which point I'm done. So.
Yeah. But I was lucky. Even that little cheap one I bought seemed to last. Well, not as long actually. It's a good point actually. But it worked okay-ish. But maybe it was below freezing though. Yeah, if it's below freezing, things are weird.
And I went to sleep.
Yeah. It's like nuts, but yeah, but like I said, you can put this outside your house on the front lawn, and hurt your house Wi-Fi, and be inside in bed, and hopefully no one's out front stealing it. That's what I'm probably worried about. But yeah, it'll shut down when it's low powered. Just the head goes back down. You got to pop off the dew shield and it just falls on the ground, and neighbors will go out in the morning like, what? What's that? So, but it's and even better if you have the S30 up here, like something an adapter, put a little battery pack next to the S30. It's even smaller and cuter. Aesthetically pleasing. But yeah, I'm waiting to get the S30 because that's going to have a better chip and a wider field, and we'll see. Because I can't imagine coming out 2 new devices per year. You're going to try to spread at least 1 year, right? So I got a feeling, the upgraded Pro version just might be next year. Who knows? End of the year. I'll have to see. But it's definitely an easy way to access astrophotography or just exploring the heavens. You can look at your maps and stuff, and then they try to, like I said, the internal maps even have a little bit of a description of the object you're looking at. Like I said, like here, right? And you click Saturn, so here's Saturn, and a little description of it. And some of the other devices actually, we have more higher-end programs we use for our sky maps and stuff, and some of those, like Sky Safari, are hooked in with, I think, Celestron's package and stuff like that, so they went bigger, badder, but it's not that bad. Not that bad at all.
Oh.
Wait.
And we all have like 9 of us. Sorry.
Yeah. Well, I was just gonna say, if you have any other questions about seestars and EAA, feel free to come up. I'm sure Keith would be happy to answer them.
Yeah.
But sure. Yeah.
Hi, my name is Andrew. I did the International Observe the Moon Night presentation yesterday. I just wanted to remind everybody tonight is International Observe the Moon Night. There are pamphlets up there if you're interested. They show a lot of different features that you can see on the surface of the moon, and then we'll probably have the moon in one of the telescopes up there, probably the 6 or something, and you can see it there. And encourage everybody to look, especially on the live stream. If you're out somewhere else and it's clear, definitely would look at the moon if you are able.
Good. Thank you, Andrew. All right, so at this point, we are going to go on a dinner break until about 7 o'clock, where we'll have Sasha Zaleski, a Kopernik educator and KAS member, give a talk on her experience and research experience at Green Bank Observatory in radio astronomy. So we'll see you back at 7, and have a good dinner.
Good evening, and welcome to we're on the final lap here of AstroFest 2025. Actually, we have 2 laps here to go, I guess. 3 if you consider the observing afterwards. But anyway, it's been a great weekend, starting yesterday with a number of outstanding presentations. The skies really did a wonderful thing for us. I don't think it's been a long time since we've had an AstroFest with 2 clear nights, let alone even 1 clear night. And but today we had again another great list of presentations, great engagement, a lot of engagement on the live stream as well. And we're going to finish up with 2 more presentations, starting our first presentation here will be by Sasha Zaleski, who is one of our educators, who spent a little time down in West Virginia. And I guess it's almost heaven down there, right? Oh, all right, I'm aging myself. Thank you. There, so sorry, I'll stop talking now. Anyway, so Sasha spent some time doing some radio astronomy, and I'll go get my Yagi for you. All right. Give it a second, I have to turn it on. No.
All right, can everyone hear me? Yeah. All right, perfect. So I think Drew kind of covered my little intro here. So I'm currently a student in college, and through my transfer from a community college to now Binghamton University, where I'm studying physics, I had the opportunity to participate in the Educational Research and Radio Astronomy program down at Kopernik Observatory. And we're going to talk about that a little bit, but first I want to speak a little bit more about why we observe in radio. So I'm sure many of you are familiar with the electromagnetic spectrum. Light is part of it. And we can actually see it right here. So this is the visible spectrum. This is what we can see. Most other wavelengths of light are actually blocked by Earth's atmosphere. And that's great for us because we don't want to be blasted by gamma rays, right? Every single day. You might be familiar what blocks UV light. Anyone know? Ozone, yeah. So that helps keep us safe. And we adapted to be able to see visible light. But you might notice here, a different wavelength of light can actually reach Earth. Quite a big portion of it, actually. And that's radio. Now, our eyes, well, we as humans didn't adapt to observe radio waves. But why? The reason for this is because our receptors, our eyes would have to be absolutely gigantic for us to actually be able to see radio. So that's why we adapted to observe visible light, which is just a little tiny narrow band, and we do get a little bit of UV and a little bit of infrared. But if we want to observe the other wavelengths of light, we got to go up to space. That's why we have telescopes that are able to observe different wavelengths of light. For example, Chandra, back there on the wall, observes an X-ray. Hubble is primarily visible. We have James Webb observing an infrared. So we have telescopes out in space that can see wavelengths that we can't. But otherwise, radio, we can do here on Earth. And another benefit of radio, we don't have to worry about clouds. So a lot of you in this room are optical observers, right? And clouds will shut down your observing, unfortunately. But radio, the only thing that will really stop it is lightning. So you can observe during daytime. You don't even have to wait till night. You can observe daytime, and you don't have to worry about any clouds. So how do radio telescopes work? Well, they're typically the most efficient shape is a parabola to be able to observe. Same with telescope mirrors in general. And there will be a distant radio source that you want to observe. And it will kind of bounce off the dish and meet at a focal point. Now, sometimes receivers for radio telescopes will actually be at the top, but otherwise there might be a secondary reflector, typically in the form of a mirror, that will then send the signal down into a feed horn or the receiver. And this is typically a funnel of different sizes based on what frequency you're trying to observe.
So the receiver has to be changed every single time you want to observe a different frequency of light. Now for the dish itself, it only has to be about as precise as it has to be a little bit smaller. The precision has to be just a little bit smaller than the wavelength you're trying to observe. So it doesn't have to be a super duper smooth surface. So for example, one of the telescopes that I used down at Green Bank was actually made of a mesh. And one might think, oh, the waves might go right through there or they'll get messed up. But no, the wavelengths are big enough that they'll actually just bounce right off that mesh. The Green Bank telescope is pretty precise, but that's because they use it to observe very small wavelengths. And we'll talk about that telescope in just a little bit. Now, as for the resolution or the beam width of the telescope itself, that can be found by dividing the wavelength you're trying to observe by the diameter. The bigger your diameter, the better your resolution is going to be. And we can kind of cheat the system by using something called an array. So the Green Bank telescope is about as big as you can safely get with a radio telescope before it might become a bit of a hazard. The predecessor to the Green Bank telescope was their 300-foot radio telescope, and it actually collapsed on its operator. For some reason, they decided to build the building for it right underneath it, and it was only meant to last really 5 years. So I'm not sure why they thought that was a fantastic idea. The operator was fine, supposedly. He was sitting there doing observations. Something crashed to the roof, and he thought, oh my gosh, something fell off the telescope. I gotta go tell someone. They come back, they're shining lights. There's no telescope. It's gone. And it was all on top of the building. You can find images of it online. So that's why we don't try to make super duper large dishes, because it can become unsafe and unstable. And also, gravity starts to play a part. But we'll talk about that when we get to the Green Bank telescope. So one way we can get around this is by using a telescope array. Because if we set these telescopes, typically a Y shape is pretty good, although recently I've been hearing that they're doing spirals, and that seems to work a little bit better. But they use interferometry to kind of make it work as one single dish. So the telescopes will detect the waves as they come in, and we know the distances between them and how much time there is between those observations, and there will be a little bit of overlap there. And so we can work around that and essentially use it as one big dish to get an image. So that diameter is now the diameter of the array, and that's how we can get a much better resolution. These telescopes can also work standalone too. I'm not sure exactly what diameter these scopes are. This is from the Very Large Array, or the VLA. They're very creative with their acronyms. It starts getting a little bit crazy, like Very Large Telescope, stuff like that. But we won't be going too far there. Now, before we get to Green Bank, I do want to talk about how we started doing radio astronomy. And it really all began with Karl Jansky. And actually, the unit for flux is named after him. And he's dubbed the father of radio astronomy. So he used to work for Bell Labs, the telephone company, and he built this antenna not as a telescope. That was not his intention. He was trying to catch static interference for his lab, and he ended up picking up something else. He picked up emission that seemed to come from space. And he actually played around with this a little bit, and he determined that it came from the center of the Milky Way. And he published a paper on this in 1933, but it didn't really go anywhere. No one wanted to invest in this. It's the Great Depression. There wasn't money for it. Radio waves in space. No one wanted to go there. So his findings kind of died down. No one really looked into it further. So there's a little bit of argument whether he is truly the father of radio astronomy or the next person we're going to talk about. But I did want to highlight that his antenna, it is currently at the Green Bank Observatory. Now this is a replica of it. It uses Ford Model T tires, if anyone was curious. Supposedly it was the original at some point, but it's been rebuilt so many times that it's now really just a replica. And this is actually my group sitting on it. It used to be functional up until recently. They did decide to stop using it. Now, his experiment was then later picked up by Grote Reber. He read Jansky's publication, got very interested in it. He even applied to work for Bell Labs. He applied to work to several other companies because he wanted to figure out what this was. No one else was doing it, but unfortunately, he wasn't able to get a job there. So he applied and settled for working for a radio company in Chicago. And he decided to take it upon himself to build his own radio telescope in his backyard. Now again, this is during the time of the Great Depression, and also it started to freak a couple people out, because if you see your neighbor building a 30-foot dish in their backyard, you might think, oh, are they trying to talk to aliens? So there was a little bit of concern there. But he did confirm what Jansky observed. And he also created the first radio map of the sky. I think it had a 12-degree beam width. So he spent a lot of his time, free time, just mapping the sky. And originally, when he built it, it didn't have this kind of merry-go-round where it was able to turn. So I think it only moved up and down. And this is Grote Reber with his telescope, where they moved it from his backyard in Illinois over to the Green Bank Observatory. So this is my photo of it right here. And it's really cool that you're able to just visit and see these historical telescopes, which leads us to Green Bank. So this here is the GBT, or the Green Bank Telescope. It is one of the largest moving things on land. I say on land, aircraft carriers are not on land, so they don't count. But it is an absolutely massive telescope. Pictures really don't do it justice. When I was driving up and I saw it pop over the tree line, it's really amazing just seeing it there. And back here you can also see some of the other telescopes. That there is the 140-foot. I will talk about it a little bit too. It's just a really, really neat telescope. And right above it, that little tiny guy, that's the telescope I was using. So, not as impressive, not as big, but I promise it's still cool. Now, the GBT, it's so big that gravity, actually I do have a little scale comparison here, just to show you how big it is. But it has about, if you notice in that original picture, these are actually panels, it's not a single dish. And when it moves, it's so large that it actually, those panels kind of get distorted by gravity and temperature. So there's about 2,004 of them. And underneath those panels are pistons that actually will reposition it and adjust it so that it's one single dish again. So it's a very, very amazing piece of technology. Unfortunately, when I was there, the GBT was being repainted. So it has to be repainted every single year, otherwise it starts to rust and fall apart, and it hasn't been repainted in 5 years. So they were sandblasting the arm. Supposedly they say that they scheduled, the little running joke is they scheduled my week specifically while the GBT was out of commission because we produced so much radio noise that they didn't want to deal with it. But that's just a little running joke there. And you may have noticed some of the pictures that I've been showing you are very grainy, and they have this little white spot on it. And there's a reason for that. It's because I was using a film camera, and it happens to have a pinhole in the curtain, the shutter anyway. But there's a reason for this, because you are not allowed to use digital cameras near the GBT or past the radio the radio instrument zone. So around Green Bank, there's about a 13,000 square mile radius where there's no cell service. There's very little use of things that produce radio waves. I knew I entered West Virginia when my cell service cut out. So at least I knew I was approaching the right place. Very unfortunate trying to find a gas station, by the way. But as you get closer to Green Bank and the Green Bank telescope, the restrictions get a lot stricter. So for example, when I arrived, I was told not to light up my phone outside of buildings. You're not allowed to drive your car really near the telescope, and actually leads here. So if we're not allowed to have these things, can we use Wi-Fi and Bluetooth? And the answer is no. So we had to leave any devices that use Bluetooth off. So you have to think about things, even like your watches, your earbuds, right? All of that stuff uses Bluetooth, and all of that stuff, so incredibly loud for those telescopes. Your phone is 1 billion times brighter to the GBT than Andromeda, for example. So it will completely just block out anything there. So this is our classroom and bunker 40, which I'll talk about a little bit more later. And you might see a huge amount of cables all over that table. That's because we were using Ethernet. So I feel like I was really going back in time. The camera I was using is a Soviet film camera. It's called a Fed 2. It's about 70 years old. I pulled out a Soviet watch, had to use Ethernet. So started to feel like I was going back in time. But honestly, I really enjoyed it. It was nice to not be on your phone all the time and having it with you. So you just leave it and forget about it. So I actually don't have too many pictures from Green Bank because I don't have that convenience of using a cell phone all the time and having it. I had to be very precise with the 30 frames I had on my film roll, right? Do you have a question? Mm-hmm.
Were you air-gapped, or did you have some sort of connection with you?
They had ports just there in their classrooms for Ethernet. So I'm not really sure how that was all set up. That was done by the coordinators of the program before we got there. So we just kind of showed up and plugged in our laptops because we did have to do actual projects. So that's, I think this might have been on crunch night. I'm not quite sure. So anywhere we're using technology was typically inside. And actually, I'm hoping this is the next slide. Yes, it is. At Green Bank, a lot of the rooms are Faraday cages. So this prevents radio waves from coming out of the room. And I cannot find a single picture of this online, but their computer lab has these 2 big vault doors. So you feel like you're entering a bank. You have to slide this giant bar to unlock it, enter the next room, close the door, and then you can open the second one to get into the computer lab. Even the windows have a special mesh on them, and it's just lined with metal. And inside their science center portion, you can actually see there on that roof all that shiny material. So that's part of the Faraday cage. And they have those big vault doors, but it's right behind here. So fortunately, I didn't take a picture of myself because I never had my phone on me. And I couldn't find one online. But this is one example of one of the huge Faraday cages they have there. And bunker 40 is another example of that too. So how about vehicles? Well, when you're kind of going towards the telescopes, by the way, there are plenty of nature trails there, so people just come there and walk or bike. But you will see this sign where it says authorized diesel vehicles only. Now, I'm not a car expert, but from my understanding, gas cars kind of produce a spark, and that will be picked up by the telescopes, so they use diesel vehicles instead. And from my understanding, I believe they somehow shield the computers in those vehicles, so they have to be the specific ones at the observatory. This is what they used to use, this blue checker here. Unfortunately, I don't think it runs anymore, but it is sitting up front, and I thought it looked really cool, so I took a picture of it. And that's what they used to get around the observatory. Right now, they have a fleet of observatory trucks. We were actually given a Ford Excursion with my group. You could sit about 9 people in there, plus 4 in the trunk if you try real hard. Otherwise, you can ride bikes around the campus. And all of those are okay to getting around the observatory because the GBT, I think you can see its arm right here. It's about half a mile away from the beginning area there where the classrooms are. Now this one was a little funny. This was in our cafeteria, and inside of that miniature Faraday cage is actually a microwave. So the microwaves have to be in little jail cells to work. Supposedly there was a guy at Green Bank and his whole job was just finding out who has a rogue microwave somewhere out there in Green Bank to make sure it wasn't bothering the telescopes. So that was just a little funny something. I didn't even notice it until a couple days in. One thing about the program, we were very sleep deprived the whole time, and we'll talk about why a little bit later. So how did I end up at Green Bank? Well, at my community college, I decided to take an astronomy class. I worked here, so I figured, you know what, I should really take an astronomy class because this is super duper interesting to me. And during that course, the lab section actually allowed us to use a remote telescope network to image. So that's really cool because I got to use telescopes that were around the world through this program called Skynet. Now you might be thinking, Skynet? Not this one, I promise. We were using the Skynet Robotic Telescope Network. So no Terminators, although the program that they used to run the telescope, they did name Terminator. So there's a little joke in there. But we use the Skynet Robotic Telescope Network. And the main point of Skynet is it's an educational program for students, even researchers. So there are professional astronomers that use this too. And it gives students the opportunity to image with actual professional telescopes. And these are two of my pictures that I took with it, for example. This was my first ever color image that I ever took on that network. These were both taken with telescopes down in Cerro Tololo. So the main Skynet telescopes are called the Prompt telescopes. And so this was taken on Prompt 6, and this one was taken on Prompt 7. This is the Tarantula Nebula. If it's unfamiliar to you, it's only visible in the southern hemisphere. So it did give me a little advantage that I could actually image objects that I can't see here, which is pretty cool. And Skynet also has a telescope at Green Bank. And that's their 20-meter telescope. And this is actually one that I got to use during my time in ERIRA as well. So, as well as part of my course. So sometimes we would do visual observations and a radio observation, and we could kind of layer them on top. And we actually did a project with Andromeda where we layered a velocity map on top of it to see which side of Andromeda was moving away from us. So red shift, blue shift. And that was pretty neat. So this is the Green Bank 20-meter telescope. Now this is my group with the Educational Research and Radio Astronomy program. It's, I'll just call it ERIRA for short here. It is led by Dr. Reichert down at UNC. So most of the students are actually from the University of North Carolina at Chapel Hill. There were 4 students from outside schools, including me. And this is honestly one of the best groups of people that I could possibly spend a very sleep-deprived week with. Very, very smart students, and I learned a lot from them. And it's really good to be with a group of people where you could just start talking about science or something you're passionate about, and everyone wants to listen. So it was a really fantastic group. And right behind us is our 40-foot telescope. If I accidentally call it the 40-meter, I mean 40 feet. They tend to switch them quite a bit. And you can actually see right there, it has that mesh material. And right next to it, you can't really see it quite too well in this picture, but this is the bunker. So it actually goes down into the ground there. And that's where the controls for this telescope are. And at Green Bank, it is primarily used for education. So they do, I believe they actually offer all students in West Virginia opportunity to use this telescope at Green Bank, which is pretty cool. And all over the walls of the bunker, there were little papers where students would write what school they were from, what they might have been observing, if they were on a team. So, for example, in ERIRA, we were all set on teams. You could put what your project was. So, oh, here's a photo of Bunker 40. And you can see those papers there. So that's actually my team, Team Gamma. We spent quite a long time in Bunker 40. And the controls for the telescope are right here. So the 40-foot telescope, it only moves up and down. It can only see north-south. So to take observations, we had to rely on the motion of the Earth. So one of my projects, I'm not sure which one I talked about first here. Okay, we'll talk about this one first. So my project with Team Gamma was to observe Cas A. This is one of the strongest radio sources in the night sky. And there is actually some other interesting stuff that made it into our image that are not actual radio sources out in space. Cas A itself is right here. These little things here are other star-forming regions. This might be Tycho supernova, I'm not quite sure. But here, you might notice this thing and this thing, quite similarly, this thing right up here. Really bright, right? Does anyone have a guess as to what those things might be? They're really annoying in visual astronomy too, I'll give you a hint. I think I heard it. Satellite? Someone say that? Yeah, we got photobombed by satellites. And unfortunately, if it's a north-south satellite, that means our telescope hits it several times. So I actually have a little scroll chart here. So one of the things that we had a digital version of this as well, but in the 40-foot telescope does have a scroll chart. And on here, you see it picked up a radio source right here. That's actually the satellite. And you can see when it goes up or down, it hits it, goes down, hits it again. So we hit it several times. And when we put it into a visual form, it shows up right here. And it kind of almost has this little diagonal shape to it. But what's really interesting is using this image, the program we used, Radio Cartographer, we used the 30-year-old version of it. If you do use Skynet, you get to use the much newer version, which is quite nice. But it lets us see what the right ascension and deck were. And what we can do with this information is we can determine the orbital period of the satellite. So that's exactly what we did. Don't ask me how to do the calculation because I hadn't slept in 37 hours when I saw it, so I can't read what my notes said. But we were able to determine that it had an orbital period of about 11 hours, and we were even able to find out which satellite it was. I don't quite remember, but I do know it was a navigational one. So that was pretty neat. And we did get hit with a couple more satellites there. Now these little lines, these bands, that is RFI, or radio frequency interference, which is absolutely horrible to have on your data, and that's why Green Bank is where it is. That's why it's in that national radio quiet zone, is to reduce all this RFI. Because if we had people with cell phones, with Bluetooth, with all this and that, if we had radio signals all over the place, our data would just be covered with these lines. And interestingly enough, during one of my other observations, we had just done a shift change. So my group came down to observe and the other group was leaving. And suddenly on our data, we just started seeing all this crazy spiking. And we're like, what is that? Like, what did we hit? Is this like a super strong radio source? Is there a satellite? What's going on? But it was just so bright. The scroll chart just went off the chart. So we popped it into Radio Cartographer, saw this giant band. We're like, that appeared right when the other group went out. Someone either had a phone on, had an AirTag, or their AirPods, and they didn't turn that all off before they left Bunker 40. And that's not even super huge telescope like the GBT. This is a 40-foot telescope, and it completely just wiped out our data, right, for that given moment. So just an example of how bad RFI can be. And part of why Green Bank was built the way where it was is because it's in a valley, so it's even naturally protected from RFI. So mostly it's the responsibility of the people at Green Bank to avoid that completely. And I would say we did a pretty good job, minus someone had a really, really noisy Ethernet port. But we figured that out while doing one of our Yagi experiments, actually. Oops, I went too far. We can go back. Oh, went too far back now. Was lagging a little bit. Gonna give it a moment. There we go. So here's the scroll chart, and this is actually a picture I took this time with my DSLR. Since the bunker itself is a Faraday cage as well, we are allowed to have our cameras in there. As you saw, there was a computer in there, and that's actually this one right here. So I was able to take a photo of it. I even took a video, and we all got super excited because it was the first thing we'd seen for a while. And we were in there for about 4 hours doing that observation from, let me see, I have the schedule, from 1 a.m. to 4 a.m., 4:33 a.m. actually. So it was the longest observation of the night for Cass A. And at the end of it all, since there were several other teams, not just mine, we were able to create a radio map of the night sky. So right up there is my group's Cass A image. Right here is the galactic center. Unfortunately, I forget what is all over here, but I do want you guys to guess what this object right here might be. Not the North Star. This is a super duper bright object. It's not the space station. Think daytime. Subjects. It's the sun, yeah. So you can just see how crazy bright it is. And Jupiter, I think, is somewhere in that image too. Jupiter was extremely close to the sun. What's interesting is the sun's so bright you can even see a little bit of, I don't remember exactly what this was called, but you can see one of those spikes in someone else's image, which was pretty cool. So that was the whole of Erira's main image. Now, as for some of the projects we did, there was about 14 that you could sign up for. Well, we were encouraged to pick 3 to 4 of them and then actually end up doing only 2 to 3. So one of mine that I signed up for was mapping the Milky Way from 0 to 90 degrees. And this was using our 40-foot telescope. So this is kind of, ignore that other stuff there, but we're observing this little quadrant of the Milky Way. And we created a really cool diagram of it. But basically, what we're doing with that telescope, remember, it only can see north-south. So this telescope, we would move it north-south, but then we would have to, again, focus on the rotation of the Earth to help get different sections of the Milky Way. So what we did was we had to create a giant list, convert galactic latitude to right ascension, and then we created a list and had to time our observations every single night to make sure that we would be able to get all of them. So we couldn't get 1 degree and then go to 2 degrees right after that because they would be too close together. We would already be passing the 2nd degree when we need to get to it. So we had to stagger them out a little bit. And that's also where that 20-meter telescope came in. So if there were any we missed, we ended up just putting observations in for the 20. So we didn't have to worry about getting them. But over the course of about 4 days, we were mapping the Milky Way. And here is Bunker 40 again. This is actually the same picture I had before, but this is our group's first mapping of the Milky Way. You can actually see it here. Every time we pass through an arm, there's a little peak on the chart. So part of what we were doing was actually trying to determine which one of these peaks was the most redshifted. So here's a little diagram after we actually processed the data that we received. So this is kind of what it looked like. And then using this information, we basically took all of these diagrams. It's a little hard to describe, but imagine them kind of being turned like this. And so we're mapping them by their velocity, by their longitude, and by their intensity. And we can create this, which we dubbed the awesome plot. So this is an LV diagram of the Milky Way. One of our teammates, who is really good at coding, unlike me, put this together for us. And this, by the way, is mapping at a frequency of 1,420, which is associated with hydrogen, cold hydrogen. A better way to map this would actually be using carbon monoxide because stuff loves to stick to it. And here's an example of that. So this is the awesome or awesome plot, as we called it. We were very tired once again. But right here, this is a lot more precise than just using hydrogen. So this is using carbon monoxide. However, the super duper cool portion of this is if we look at this section, right, from 0 to 90, right here, we can fit our data right on top. So, and it fits pretty well, which was super exciting. But there is the mapping that we were doing of the Milky Way. So it would be more precise if we could use carbon monoxide. Unfortunately, our telescope didn't go to that frequency. So, oh, I'm not sure why I put that image in there again. All right. The next one. All right. As for the 140-foot scope, we didn't get to use this one, but it is super cool to talk about because this is the world's largest equatorial mount. So back when this telescope was built, it was a lot easier to just use an equatorial mount. And inside is also a ball bearing that is about 17 feet in diameter. I did look it up. It is no longer the world's largest ball bearing, unfortunately. But it still holds the title for world's largest equatorial mount. And unfortunately, it is not in use anymore. Its last mission was in 2019, navigating a Russian satellite. But we did get to tour this one, which is why I put it in there, because it was just really neat to be able to go up on this platform. So here's an image of some of my group mates from Arira, and we're looking out on the GBT from it. And it has a very naval-inspired design because it was built by naval engineers using salvaged submarine parts. So it's a pretty unique telescope with a pretty unique history. So I did just want to highlight that as well. All right, now for my next project. It was dubbed Instrumentation Antenna. And we had a radio Jove kit, which is really meant for observing the sun or Jupiter. Unfortunately, the sun and Jupiter were right next to each other, so we couldn't observe Jupiter. At any time, supposedly, they've tried to do anything with the sun, it was a disaster. So they told us, we're giving this to you, you can do whatever you want. So we set up our dipole, and we just let it sit there. Weirdly enough, we ended up getting this. Can anyone guess what this might be? These really, really large bands here. Solar flares, yeah. So this year we caught not 1, but 3 solar flares. On previous years, when they were never able to do anything with the sun, we got hit with 3. And this one was really, really cool. And the even better part, we were able to confirm it too. So our first solar flare was confirmed by 5 different sources, I believe. So that was really neat that we were actually able to observe them and then be able to see it just pop up all over the place, that other people saw it too. Now, during this time as well, we, oh, not quite yet. One more thing. So as well with our dipole, quite interestingly, we picked up a radio station from Texas, which you're not supposed to be able to do in West Virginia. So funny enough, I can actually play that recording here if it works. Oh, that was not good. Really? Yeah, it just went to the next slide instead of playing it.
Support for Tacos of Texas comes from HEB.
Wherever you are, at the gym, in the waiting room, or in line at the store, stay up to date with the TPR app, which lets you listen live or on demand to catch something you may have missed. The TPR app alerts you to breaking news, local stories, and episodes of your favorite shows.
All right, so I'll pause it there. But you heard from the get-go, Tacos of Texas, right? So, our coordinator for this particular group, she was just sitting there listening to it and went, huh, that's weird. So we were trying to figure out what might have caused this, and the theory is sporadic E, and truthfully, we don't really know what that is. But the current theory is when that E layer of the ionosphere, it becomes ionized, and it allows these waves to just propagate and go much further than they should. So they're just kind of bouncing and bouncing and bouncing, and they're just flying real nice and far. Yeah. So that station we actually found was from Ingram, Texas, which is 2,000 kilometers away. So pretty far. So that was really neat to observe. Now, one of the projects that I suggested we do, we had access to a Yagi antenna. Is there any hams in here? I see Drew raising his hand. I know there's got to be a couple more. All right, well, if I say something wrong, don't correct me until after the program, okay? But basically, while I was there was actually during the Perseid meteor shower, and it was cloudy every single night, which I heard it's clear up here, which I was really mad about because I swear it's never clear up here when I'm here. But anytime there's something cool and I'm not here, it's actually clear. But I thought, listen, radio waves can travel through clouds, right? And actually, last year when I was observing the Perseids here, I don't know if Mark's in the room, but he brought out a radio. Oh, there you are. You gave me this idea, so I give you credit. You mentioned that we could listen to the Perseids. So I was here at Green Bank, and we had the option to do whatever we wanted. And I said, listen, if we can't see them, why don't we try to hear them? Because we have radio waves, and they bounce off these ionized tails off these meteors as they fly above us, right? So that was the idea. And here's actually my group with our Yagi. It's actually the same one as this one here, so thank you, Drew, for letting me borrow this for a second. We didn't end up using that other antenna on the table, so just ignore it. But the Yagi is a directional antenna, and we did move it around quite a bit to see if maybe we could pick up signals a little bit better somewhere. But we ended up just pointing it at the building, the Science Center itself, to see if it could kind of work as a reflector for us. So we were standing there like this for a really long time, just seeing if we could hear something. And the way it works is you tune to a really distant FM station. So we tuned to one, it mostly just sounded like static. You could kind of hear someone talking, maybe some music playing, something like that. So we just tuned into one, and we sat and we waited for a really long time. And what ended up happening was we were sitting there, and this is what it looked like. On my screen, we used an SDR, software-defined radio. And you could hear these were a little bit clearer, so we didn't tune to those. So I found one which was about 89.7, and we were just sitting there listening to kind of static for a pretty long time. And I will say, it's West Virginia, so a lot of the stations are gospel music, so just letting you know that for the next part. Because while we were sitting there, we ended up hearing this all of a sudden. Let's see if I can get it to work again. And it suddenly clears up. And then it disappeared. But right, but that sudden clearing up, that was that meteor flying over. So when one flies over, suddenly that signal will become a lot clearer. So that we didn't change frequencies, we didn't do anything, we just left it. And you actually kind of see all the frequencies just light up there for a little blip. And this particular one didn't pertain to this audio file because we were so excited we actually got one. I forgot to actually screenshot it and press record. But it was more important we got the audio file. So we observed about 3 of them. This was probably the best one of them all. And this can actually last up to several minutes depending on what meteor you got. So that was really neat to observe because since we weren't visually able to see the Perseids, it was really cool that we could actually hear them. And with that, I'm going to conclude my presentation. So I thank you all for coming and listening to my little experience here at Green Bank. And if anyone has any questions, I may not be able to answer ones that are super specific about radio, but I will do my best. So does anyone have any questions? Yes, we do need the mic for the live stream.
Do you plan to go back again for another course?
I would love to if I have the opportunity. Absolutely. It was one of the most unique experiences of my life, I would say. I really enjoyed it. I got to meet a lot of really neat people, and I got to do some real science, as my professor would call it. So absolutely. And also I just really enjoyed being there and just being in nature all the time. It was great. Any other questions?
How did the radio waves get converted into the visible light images you were showing us?
So that was all done through that program called Radio Cartographer. I'm not exactly sure how it works, but my guess is it bases it off. So the different colors relate to the flux. So the greater the flux, the brighter the color. So for example, let me see if it will go back or if it will lag. I really want to show the Cassé one because that was the best one. Too far. But it corresponds to basically the flux. So that's how it would work, where the telescope picked it up, essentially. I'll just go with this one. So in the sun here, it's very, very bright. So in that, oh, it's not cooperating with me, but you saw how the center was very bright, right? And the lower the flux, the darker the colors become until they're eventually black. And what's interesting is you could actually click on places. So for example, we knew where a radio source had to be. So we had a list of radio sources and we knew that they might be in a specific location. So even if it doesn't visibly show up here, at least not as a really bright spot, we could click where we know it's supposed to be and it would show you a magnified view and you would be able to measure the flux there. And our numbers were pretty close to that source list, which was really cool as well. All right. Any other questions?
Wait a second, Art.
When you observe the solar flare, the aurora, do you have a lead ahead when they're coming? Do you can you see it that they'll be coming soon, or they just show up?
I don't think we knew they were gonna happen. We actually saw them before they were confirmed. So it seems that we were catching them either around the same time everyone else was, but no, there was no prior indication that we were going to see a solar flare. It did seem that the sun was particularly active during that period of time, though, based on that we've got 3 solar flares on 3 separate days, though. So.
All right, got a question over here.
How far into deep space can radio waves be detected?
Very far. So we can detect, so cosmic background radiation, that's basically from the Big Bang. And we're able to detect that kind of residual radiation there. So we can see pretty far. But there's also just stuff kind of flying around that we're able to pick up. So. And some telescopes, they can also transmit. So for example, if we're trying to observe a specific body in space, we did have a presentation that talked about how an image was taken this way by sending out waves and then having them kind of bounce back and collecting that information from there. So sometimes we do that. If the radio telescope can transmit, we will use that method as well.
All right, any other questions? All right, well, Sasha, thank you again. Now that you've caught the RF bug, I'll have to give you the ham radio license manual, and we'll see if we can get you licensed. So what we're going to do now is we're going to just take a small 5-minute bio break, and then have everybody come on back. Our Director of Education, Dr. Laura Lamache, will be telling you a little bit about Kopernik, and then we go to our featured keynote presentation, Andrew Fox from Corning Glass Advanced Optics. So let's be back right at 8 o'clock. And we're back. We're closing in on our final presentations. I'd like to introduce our Director of Education here at Kopernik, Dr. Laura Lamish. She's been an extraordinary. We have great, extraordinary resources out in the domes. Well, I'm standing next to an extraordinary resource, and she's going to tell you a little bit about Kopernik and the work that we do.
Well, good evening, everyone, and so thank you. So I am working here as the Director of Education. I'm also a member of the Board of Directors. So I wear many different hats, but I wanted to take a moment to just welcome all of you and to thank a lot of people responsible for AstroFest. So I spent some time making a list, and I hope I got everybody, but often what happens with lists is you leave some people off, but I think this is pretty comprehensive. I drew check it. But a lot of work goes into these evenings, and I want to especially thank Art Cassiola. He's been working so hard for weeks now, so thank you, Art. We are so blessed with so many great people here, and most of these people are volunteers, but I just want to highlight, our Kopernik staff that's here, that's been working, and thank you, everybody. I want to highlight our Kopernik Astronomical Society members who have been running the scopes and who are a real life force here at Kopernik. I want to thank our presenters, and I really also want to thank all of our interns and helpers, all the young people you've seen walking around, working the register, working coffee, checking you in, checking you out. It's just been a great collective effort, so thank you, everybody. And as I look at this list, I want to just take a moment to talk about what a special place we have here. So a lot of my work involves building programs, working with school groups, and bringing a lot of young people through this space. And along those lines, I want to share with you, let's see here, something I read a lot, which is our mission and our vision. So Kopernik Observatory, we're in our 51st year. So we opened in 1974. Okay, we started getting built in 73. Okay, we had a renovation in 93. So this is our 51st year. And, this is really important what our purpose is. All of the people that have made AstroFest happen, it's that spirit of volunteerism that's been keeping us going for 50 years, for 51 years. And it's the spirit that drives us to keep working hard. But I want to point out to you that as I look around the room, I see people of all ages. And one of the things I find very special about Kopernik is that we're multi-generational. And you feel that when you're here. And I just was, with Sasha's presentation, it's so inspiring to see young people stepping up and taking on leadership roles. And Kopernik has done that for generations now. One highlight I want to make then is over the last year, we've been working very hard to bring school groups in. And last year, we had the highest number of school group participation, I would say, ever, Drew, in our history. Over 3,500 students we served last year from 18 school districts, okay? That's big for us, and we're growing. We're continuing to grow, trying to get young people in who become people like Sasha and Jenny, who's in the back there running the show. But, so Jenny's back there. But, so a lot of our work is to really inspire young people. So I just want to make a point of a statement in our mission. Kopernik is a place of exploration, discovery, and inspiration for inquisitive minds of all ages. I think what AstroFest represents to me is that spirit. So, I just want to say things are very exciting here. We have an annual campaign coming up, and please pay attention to your emails and to our Facebook and social media posts, because that campaign is very important in terms of continuing our growth as an institution. I think, Drew, are we good? So I want to thank you all for being here, and please pay attention to Kopernik as we continue to grow. And again, thank you, everybody, for helping out tonight. Yeah.
Thank you, Laura. All right, we are going to take a moment to get our presenters' laptop connected in here. So give me a moment as we switch computers. Ooh, on the right side. Let's see. Ooh, worked the first time. Excellent. So, one of the things I really love about Kopernik is our Friday night programs, where we have an opportunity to really learn about various aspects of science and technology, not always about astronomy, but obviously being an observatory, what happens in the astronomy world, has a lot of interest for us, and most recently the Vera Rubin telescope down in Chile was just recently opened up, and the images coming there were just extraordinary. And I somewhere I had read about Corning glass is actually had something to do with that, and so it wasn't easy to actually get a hold of somebody at Corning, but they did call back, and ultimately they led us to Andrew, who brought most of his family down from basically up near Ogdensburg, way up north. That's where that facility is, and again, just as a very small plug here. If you are a Kopernik member, you can actually get into the Corning Museum of Glass in Elmira for free. So, just saying. But anyway, again, this weekend's AstroFest really focuses on astronomy, and we're just so fortunate to have this world-class corporation that just really makes a huge difference in our world. And so I'm going to turn this over to you, Andrew, and let us know all about Corning.
Yeah, thank you very much. You can hear me okay? All right, well, great to be here. Good evening, everybody. Thank you, Drew, for inviting me. I'm excited to be here. We've had such a fun time, my family and I. The only disappointing thing about the whole weekend is to realize that we're 5 hours away. We live 5 hours away from here. So it's going to be challenging for us to come back on a regular basis. But so I'm looking forward to sharing with you a little bit about what Corning does specifically. But one of the things I wanted to kind of highlight is one of the things I think about. I want to highlight the innovation that Corning does, which is just such a small snippet of the innovation that's enabled astronomy as a whole, right? But really, when I think about this, exploration, so astronomy, for instance, really drives the innovation that's needed for that. And in turn, the innovation that various people do enables that exploration. So there's this interesting symbiotic relationship between the innovation that's happening and then the exploration that's happening as well. So a little bit about Corning itself. So Corning's existed for over 170 years now. We specialize specifically with expertise in glass science, ceramic science, and optical physics, as well as some specific manufacturing capabilities that we have. And like I said, we have an interesting history as it relates to how we've supported various astronomy programs over the years. So this is going to be kind of a fast flyby overview of some of that history. So I wanted to go back to Eugene Sullivan. So this is a key player in Corning in the early 1900s. So actually in the late 1800s, Otto Schott in Germany invented borosilicate glass. And so then in the early 1900s, Eugene Sullivan, who was actually tasked with establishing the first research facility at Corning, he took Otto Schott's invention, he worked with some colleagues, and they worked on improving that design, improving that glass. And one of the problems they were trying to solve, unrelated to astronomy, but it's a little interesting, they were trying to solve an issue that they were having with the railroad lantern business that they had at the time. So Corning had business making railroad lanterns. They had improved the glass for the lanterns over the years, particularly with regards to the color of the glass, which made the signals much more clear for the signalmen to avoid accidents. But one of the issues they were having is the glass was breaking. So in particular, on a cold winter night, for instance, the lantern would be in a warm shed. They'd bring it outside. Maybe there'd be cold rain or snow that would hit that glass and it would fracture. So they needed to come up with a lower expansion glass. And so they took the borosilicate glass, they improved on that, and they branded something called Nonex at the time. It was a portmanteau of non-expansive. So that dramatically reduced the breakage issue for railroad lanterns and actually significantly reduced train accidents across the country as well. So they took this glass, they further improved it, and eventually branded Pyrex, which I'm sure all of you have heard of. Not only Pyrex cookware, but probably Pyrex is in some of your instruments as well, right? That became a huge business for Corning. So keep that in mind, the Pyrex. And at the same time, an astronomer in California at Caltech decided he was in the process of building some of the largest telescopes in the world, of course. George Hale, he had already built a 100-inch telescope, the Hooker telescope on Mount Wilson. And the largest telescopes, I believe, in the continental US at that time were the Hooker telescope, and then there was a 69-inch mirror at an observatory in Ohio as well. Both of those mirrors essentially used a type of crown glass. It wasn't a super low expansion. And George Hale knew the Hooker telescope, well, first of all, the Hooker telescope played a big role in astronomical discovery. Edwin Hubble was doing work there, and one of the main observations that he made, or discoveries that he made, was that the universe was expanding. So that was significant. But they did have a big thermal stability issue with the telescope. They could only use the telescope for a short period of time on any given evening before the seeing issues were just became too difficult. So George Hale decided he's going to build this 200-inch mirror telescope out of the lowest expansion material known at the time, which was fused quartz. So he actually contracted with General Electric first. And General Electric didn't really have a good manufacturing process established yet to make these fused quartz mirrors anywhere close to this size. Unfortunately, they struggled quite a bit. And after about 3 years of effort, hundreds of thousands of dollars, they still didn't have a good process established. They couldn't tell George Hale when the mirror was going to be done, how much money it was going to take. So he decided to cancel the contract. He had some contacts at Corning and knew they had this Pyrex glass. So he decided, let's work with Corning and we'll make this mirror out of Pyrex. So a research physicist by the name of George Macaulay at Corning was tasked to lead the project. And Corning already had, as I mentioned with the Pyrex cookware business, they already had high volume manufacturing established for Pyrex. The challenge was going to be increasing the size. You know, a cookware and a 200-inch mirror blank, it's a little bit different. So George Macaulay came up with a plan. The main focus of the plan was to basically slowly step up in size. He was going to make 3 60-inch discs, one slightly larger oval, a 120-inch disc, and then finally the 200-inch mirror blank itself. Interestingly, in the back of the room, there's a smaller 20-inch disc that is one of the test articles that came about from this process. So before too long, they did run into an issue. So while they were testing one of the 60-inch discs, a chemist by the name of Martin Nordberg discovered that during this much longer annealing process that they'd never had to do before with the cookware, they were running into some moisture issues with the particular type of Pyrex, the composition that they were using. So they knew they needed to modify that composition. So thankfully, Nordberg and his colleague Harrison Hood quickly developed a new version of Pyrex that dealt with that issue. That did not plague them anymore, and by happenstance, it actually had 25% lower thermal expansion as well. So George Macaulay, he decided, well, I'm not actually going to tell Caltech that we had a problem. I'm just going to tell them we're switching to this other glass because it's better, which I guess is true. So here is an image. Actually, the previous slide and this one are both drawings and sketches from an article from Popular Science Monthly in 1934. Might be difficult to see on the screen, but this kind of gives you an overview of how they actually poured the mirror blank itself. So in the top right, they needed to use a continuous tank furnace rather than a pot furnace. So that was one of the innovations that they had. They had already done that. They had established basically a continuous operating melting tank for the Pyrex cookware business. They actually used these giant ladles, which you can see in the lower right, to transfer the glass from this melting tank over to the casting furnace. And they'd pour that into the casting furnace. The glass had to be maintained at 1,500 degrees Celsius, nearly 3,000 degrees Fahrenheit. And that pouring process would take about 12 hours long to do. Very arduous effort. So they went about this trying to cast the 200-inch mirror blank. And part of the design of the mirror was to have this honeycomb structure in the back. So they poured it into a mold, and the mold had these refractory cores inside. And the plan was to pour the glass into the mold. Once the glass cooled, they would knock out these cores, and you'd be left with this honeycomb structure. Unfortunately, those cores were the weak link in the process, right? And so as they were pouring it, they could not withstand the heat and the long process that it took. And so during the pour, slowly those cores broke free from the mold and they floated up into the glass, and they knew this is a problem. This mirror blank is going to be ruined. So George Macaulay decided, well, we're still going to be committed to providing this mirror for George Hale. He got approval from Corning management to pour another mirror blank, and he decided, well, we're going to make lemonade out of lemons. So we're going to use this ruined mirror blank. We'll do some additional annealing testing and some other things and learn as much as we can from it. Here's some other photos of the process. These giant ladles, like I said, to transfer the glass from the melting furnace into that casting mold. Here they are on the left. You can see them pouring the glass into the mold, and on the right they're actually in the process of dumping some of the glass. So actually each ladle, they only poured about 1/3 of the glass at a time into the mold to prevent scale buildup. So finally they did have success, right? So you can see on the left there's the first mirror blank, as Drew mentioned, in the Corning Museum of Glass. You can go there an hour down the road or so and see that's on display. And then the second mirror blank, the good one, obviously you can see George Macaulay and his colleague there inspecting it. And this was a huge success, right? So the telescope, after a delay due to World War II, eventually became commissioned in 1949 under the direction of Edwin Hubble. And the telescope itself was named in George Hale's honor, the Hale telescope, after his death. So at the time, this was twice as large as the next largest telescope, the Hooker telescope, right? So 4 times the collecting area. An incredible feat. And it was, I believe it was the largest telescope in the world for something like over 40 years. So incredible. So at the same time, another chemist, a research chemist, James Franklin Hyde, at the same time that they were working on the Hale telescope, Hyde was actually hired by Sullivan to explore silicones and plastics, kind of a new product at the time, right? And so he was experimenting in the lab, and he tried to, he took basically a silicone salt in a vat, and he heated it, passed it through a burner, and it deposited this vitreous silica on an object, this glassy silica. And what he had discovered, or what he had invented, was fused silica. So this is, of course, one of the most pure and immaculate products or glasses, substances on Earth. It's enabled lots of products in the world, particularly for astronomy. But it's enabled things like spacecraft windows on the space shuttle. We'll talk about that in a few slides. It's enabled things like large telescope mirrors, lenses for telescopes. It's enabled things like low loss optical fiber that we use for the internet, right? It's used in semiconductor chip manufacturing, so we can get our cell phones in our pockets. All kinds of things are based on this invention from Franklin Hyde. A few years later, Martin Nordberg, if you remember, he was involved in coming up with a solution for the Pyrex glass composition issues. He decided he was going to continue with this development of fused silica, and he discovered that if I add titania to the composition, it's going to take fused silica, which was already the lowest thermal expansion substance known to man at the time, and it's essentially going to reduce the thermal expansion down to 0. And so he filed a patent in 1939 for this. It eventually became, was branded as Corning ULE, or ultra low expansion glass. And in the bottom of the chart there, you can see I've just got some of the coefficients of thermal expansion to different materials, right? So crown glass, which was used in, for instance, the Hooker telescope, borosilicate glass or Pyrex, fused silica, and then ULE. And so just for comparison, if you take, if I can get this to work here, if you take if you imagined if you had a half a mile long piece of material, if that was aluminum, half a mile long, and you change the temperature of that by 1 degree, the aluminum would grow 3/4 of an inch. So if you do the same thing with crown glass, again, a half mile long, you increase it by 1 degree, it's going to grow 1/4 of an inch. Pyrex, it will be 1/10 of an inch. Fused silica would be 2/100ths of an inch, and ULE would be less than 1/1000th of an inch. So you can imagine the importance of that. So one of the first uses of fused silica actually for astronomy purposes was in an airborne or a balloon-based telescope, so called the Stratoscope 2. So in the late 50s, Corning built a 36-inch fused silica mirror for this telescope. It was floated on a balloon at 80,000 feet for I think close to 8 years, something like that. They decided, let's bring this thing above, as far above our atmosphere as we can at the time. As I mentioned, the fused silica was used for space windows. So Project Mercury utilized Corning fused silica windows, obviously, to keep the astronauts safe. The Apollo mission used fused silica windows from Corning, so all the space shuttle windows were made by Corning, as well as the International Space Station, those cupola windows were all made by Corning. That's actually a very huge point of pride for Corning and the Canton plant where I'm from. So continuing on with some of the large telescope mirror blanks that Corning manufactured. So an 88-inch telescope for the University of Hawaii. The mirror blank, again, fused silica, was manufactured in 1970, I believe. When this was built on top of Mauna Kea in Hawaii, it was at the time was the highest observatory in the world. The Harlan Smith telescope in Texas was a 107-inch fused silica mirror blank. The telescope was completed in 1968. This one was interesting. There was an act of vandalism shortly after that telescope opened. A disgruntled employee actually came back into the observatory with a handgun, fired a shot at his supervisor. Thankfully, I don't believe anybody was hurt, and hit the primary mirror something like 6 or 9 times, somewhere in that range, and actually hit it with a hammer as well. Amazingly, the mirror didn't shatter. It survived, and light collection efficiency was only reduced by about 1%. So the European Southern Observatory built a 3.6 meter telescope, so a 144-inch fused silica mirror. All of these that I've been talking about, these mirror blanks were produced in a plant in Bradford, Pennsylvania, not too far from here. This mirror blank was 20 inches thick, weighed over 12 tons. This observatory was built on La Silla Observatory in Chile. So like I said, all of these so far have been built in a plant in Bradford, Pennsylvania. I'm not from Bradford, Pennsylvania. I'm from Canton, New York. And so Corning actually in 1966 decided to move all fused silica production and associated products up to Canton, New York. So why did they do that? So a few different reasons. One, so at the time, the precursor, the chemical precursor to make fused silica was silicon tetrachloride. And so one of the primary off gases of that process is hydrochloric acid. So where Bradford, Pennsylvania, where the plant was not very desirable for that pollution. Canton is a much more remote location, and so that was more desirable. It was also more secure for some of the government programs that were going on at the time. So since then, in the 90s, there was a big campaign to change that chemical precursor to a different chemical precursor and eliminate that hydrochloric acid pollution. Corning actually won New York State Governor's Pollution Prevention Award in the 90s to mitigate that. So a couple more reasons why they moved to Canton. So the skilled workforce, there's actually 4 universities within 15 miles of the plant up there. A lot of our operators have 4-year degrees. Low cost resources, so access to Canadian natural gas and low cost power from the hydropower project on the St. Lawrence River. And then maybe the thing that's most important, I don't know if this is true, but I'm told that the head of the selection committee was an avid duck hunter, and he really enjoyed hunting around the wetlands around the property. So sometimes it's who you know, right? One thing I find interesting, this is a local paper from Potsdam, New York, when the plant was opening. You know, a plant that's going to employ over 200 employees for over 50 years. And this is like on page 27 of the paper. So there's the plant a couple years ago, maybe. That's as it looks today. So one of the first ULE telescope mirror blanks that was built was actually for a proposed Italian telescope. So this is a 138-inch diameter mirror. Corning completed that blank in 1971. Unfortunately, the observatory was never built. I believe funding never came through. This one is interesting in that maybe about 10 years ago, we actually located this mirror blank somewhere in Italy. Corning actually purchased it back and is using it, repurposed it, and is using it as a support structure for some of the lightweight mirrors that we manufacture today. So another telescope, this one was a fused silica mirror blank, 100-inch, supplied by Corning. One of the interesting things about this telescope is, as far as I'm aware of, this was one of the first that utilized a light-weighted mirror blanks. So the secondary and tertiary mirrors for this were 60% light-weighted, made of ULE, using a high-temperature fusion process. I'll talk a little bit more about that in a few minutes, but as far as I could tell, these were the first lightweight mirror blanks for a telescope. Bring this up a little. Using that high temperature fusion process. This also had a 30-inch fused silica corrector lens in this telescope. So again, about that high temperature fusion process. So throughout the 60s, the 1960s, Corning was developing this process to make these lightweight mirror blanks. And of course, at the same time, NASA decided we're going to build a space telescope. You're all very familiar with the Hubble Space Telescope, of course, and Corning was selected to make that primary mirror out of ULE. And so Corning made two 2.4, about 96-inch mirror blanks for the primary mirror. The flight mirror blank went to Danbury, Connecticut, and the backup we delivered to Kodak in Rochester. So some of the key dates there: in 1978, the mirror blank went under what we call high fire. So the mirror blank is actually a sandwich seal construction. So if you think of, there's two face sheets in this mirror blank, the front face sheet and the back face sheet. In this case, they're both about 1 inch thick, made of ULE. And then the core is a light-weighted core. And the way that light-weighted core is manufactured is there's individual struts and posts that are fused together, almost like flame welding, fused together, and eventually, one by one, slowly constructing this core until it's this 96-inch diameter light-weighted core. Once you have the plates, which are actually made from fusing together smaller pieces of ULE themselves, so you have the two plates and the light-weighted core, that goes into a furnace for what we call a high temperature fusion process. So those are heated up to close to 1700 degrees Celsius, just to the point where the glass is fusing together. If you go too long, the glass starts to sag and deform. And so what's very challenging about this process is you actually have like a 30-second window once you get the mirror up to this temperature to decide, is now the right time? Is it fused enough that we're going to cut the burners and open the furnace doors to cool it off before it starts to deform? You don't want to go too short, it won't fuse together. You don't want to go too long, everything will deform. So that was a very challenging thing about that process. Yeah, just right. So of course, the Space Telescope eventually launched in 1990. Had the issues, of course, that it had. Spherical aberration was discovered after it had first light. That was caused by, unfortunately, the finisher in Danbury had figured the mirror to the wrong curve. They determined that an improper test setup was used when they were testing the figure of the mirror blank, and they basically made it to the wrong shape. The backup was actually, I think, made to the correct shape. That's in the Smithsonian in Washington, D.C. But Corning actually produced fused silica lens blanks that went into the corrector lens system, that CoStar system, which put glasses on the telescope, right? And of course, this is just, there's some highlights. You're all very familiar with the Hubble Space Telescope. One of the things that I find interesting is NASA's website says that they've generated over 21,000 peer-reviewed scientific papers from the observations of the Hubble Space Telescope. It's absolutely incredible. So moving on, in the 1990s, 3 large telescopes were being built. 8-meter telescopes, some of the largest telescopes at the time, ground-based ones, using a large monolithic 8-meter diameter primary mirror. So the National Astronomical Observatory of Japan was building the Subaru telescope, which is on Mauna Kea, and then that was an 8.3 meter diameter primary mirror. And then the Gemini Observatory actually built 2 telescopes, right? Gemini North, which is on Mauna Kea, and then Gemini South, observing in the southern hemisphere on Cerro Pachon in Chile. So those were both 8.1 meter primary mirrors. So the process that Corning used there, we actually made, when we're forming ULE, we form it in what we call boules. And so at the time, these were probably 60-inch diameter boules. We make even larger ones now. But they took those individual boules, they actually had to stack seal them together on top of each other to get the thickness needed for this mirror blank. And then they took 55 individual pieces, either full or partial ones around the outside, cut them into hexagons, called hexes, and then put them together in a furnace, heated it up to 1700 degrees C, thereabouts, until it fuses together. So then that mirror blank is put over a refractory mold, so it's basically balancing on the center there in that photograph. Heated up to somewhere about 1500 degrees C until it sags over that form. And then using the same 8-meter turntable that's in that furnace, we put a grinding beam on that, so they contour ground it, and actually did some acid etching of the mirror blank in that furnace turntable. So they did that again for 3 mirror blanks in the 90s for Subaru and Gemini. So here's the finished Subaru mirror blank. Here it is leaving the Canton, New York facility. I believe these got sent down the road to the port of Ogdensburg. Ogdensburg is a city on the St. Lawrence River there nearby. Went on a barge and went down the seaway to, I'm not sure if one of these was finished in France, and I think maybe one was, or some of them were finished in Pittsburgh. I don't recall exactly where, but just shipping it is a huge feat in itself, right? So the Subaru secondary and tertiary mirror blanks are there, you can see on the right. These were made with a similar process. These were actually the first frit bonded, some of the first frit bonded mirror blanks. So that's a different process than that high temperature fusion process. So they utilize the same method to manufacture the core. There's an actual photo of the struts being fused to posts, and that's how they kind of built up that core structure. But instead of that high temperature fusion process, that Goldilocks process, as Drew named it, we actually developed a frit or a glass powder that gets applied to the surface of that core structure. And you don't have to heat it up to 1700 degrees Celsius. You can heat it up to well below 1000 degrees actually. And so the glass itself is not deforming at that time. So they have this constructed core from the fusion welding, and then the frit bonding. It's how the secondary and the tertiary mirror blanks are made. So that's a 1.3 meter diameter secondary mirror here, and then this is roughly a 1.4 meter diameter tertiary mirror in the Subaru telescope. So then in the 2000s, continued on building mirror blanks using that same 8-meter facility. These were 2 4.3 meter mirror blanks. So one for the SOAR telescope in Chile, and then one for the Lowell Discovery Telescope near Happy Jack, Arizona. So those mirror blanks were delivered in 2000 and 2005. So similarly, it was a hex sealed process in that 8-meter furnace, and then sagged and contour ground and acid etched. This is a photo of the Discovery mirror blank with happy customers. So I mentioned the frit bonding process. So one of the things that enabled is even lighter weight telescope mirror blanks, right? So the Hubble Space Telescope, that style was maybe up to 80% lightweighted at the most. So about 20%, it weighed about 20% of an equivalent solid. But that frit bonding process, because you don't have to worry about the glass sagging due to the high temperatures, you can make the face sheets even thinner, you can make the struts even thinner, and get an even greater light weighting. And so the Kepler Space Telescope utilized a frit-bonded ULE mirror blank. Of course, Kepler was launched in 2009 to discover Earth-sized planets in habitable zones, what are called exoplanets. And they did that by detecting a periodic dip in the brightness of a star, which would be caused by that planet transiting in front of the star. So Kepler lasted for roughly 9 years. They discovered over 2,600 planets outside of our solar system. So here is an image of the primary mirror being inspected or tested at, I believe, Ball Aerospace at the time. So this was a 1.4 meter diameter ULE mirror. It was lightweighted to about 14% of an equivalent solid. And this was one of the early uses of an abrasive water jet to manufacture the lightweighted core. So instead of constructing that core by fusing struts and posts together, they actually have a solid, core solid, and then they cut out the little cells to manufacture that core. And so you can get much, much thinner struts by manufacturing it in this way, much, much better lightweighting. It also used a Schmidt corrector lens made from Corning fused silica that was 37 inches in size. Want to mention somebody that was key over the years for Corning and the mirror business, Henry Hagee. So he was an expert in testing glass, and particularly the thermal expansion of glass. He helped solve quite a few problems throughout the 60s and 70s with sealing processes, problems that would be caused by non-matching thermal expansion of the glass that's being sealed. And he also helped develop that frit bonding process that was key for multiple programs. So it really helped enable the Hubble Space Telescope mirror, as well as our frit bonding process that we use today. And this is actually a plaque that we have in our large mirror assembly facility at the plant that's dedicated to Hank Hagee. So Corning's been involved recently with fused silica lens blanks to support some of the large cameras that have been going into telescopes. Some of these have been supporting the exploration of dark energy and dark matter. So the dark energy camera, which is on the Victor Blanco telescope, utilizes 5 Corning fused silica lenses. The largest is 38-inch diameter, which you can see here being tested. This was polished by CISO, which is, I believe, in Belgium. The dark energy spectroscopic instrument on the Mile telescope utilizes 4 Corning fused silica lenses, the largest of which is 45 inches in diameter. And then there was another one called an instrument called Weave, which was installed at the prime focus of the William Herschel telescope on the Canary Islands. So this has a 43-inch diameter prime focus corrector lens, and a lot of those from both the dark energy camera, the DESI lenses, and then the Weave, we had to manufacture the fused silica, and then to get the shape that's needed, we actually had to sag them over a form, and you can see that process here, where we place the fused silica on a sag form, heat it up, and then there it is after it's been sagged. We'll contour grind that and then send it off. This one was actually polished and finished at a shop in New Zealand called Kiwi Star. So that brings me to, as Drew mentioned, the Vera Rubin Observatory. So this saw first light images in June of this year. You can actually access a lot of the images on their website, which is fantastic. So this is on Cerro Pachon in Chile. So the Legacy Survey of Space and Time, the LSST, their plan is they're going to capture the entire southern sky every 3 nights and do that for the course of 10 years. So you can imagine that they're going to have an incredible amount of data. So over 1,000 images of every single point in the southern sky. They'll have over 1,000 images over the course of 10 years of that same location. So they'll be able to see what's changing over the course of 10 years. They're using an incredibly wide field of view telescope that says 3.5 degree field of view. That's like 7 moons across. And it contains the largest digital camera ever built. So they're going to generate an incredible amount of data, 20 terabytes of data every single night, and about 60 petabytes of data over the course of 10 years. That's the data management plan for this telescope has got to be just amazing. So Corning manufactured the secondary mirror blank for this. So this is the largest convex mirror in operation right now. So 3.4 meter diameter secondary mirror. So we took 8 what we call petals of ULE. So these aren't hexagons, we call them petals because it has a large center hole, and fused those together. There's some of the customers there in front of the fused mirror blank. And then we sagged that over a sag form to get the right shape. And then there it is with the happy customers again during final inspection and commissioning, or acceptance rather. We shipped this blank to our friends in Rochester, L3 Harris, the former Kodak facility. They did the fine grinding and polishing. They integrated it into a secondary mirror assembly. So this was a big success. In addition to that, Corning made the lens blanks for the camera. So there are multiple fused silica lens blanks, the L1, L2, and L3, so the largest of which is 61 inches in diameter, as well as 6 filter blanks, all 6 30 inches in diameter. Those are going into this camera, or did go into this camera. So there's the largest lens blank. This is made of a single piece of fused silica. The Lawrence Livermore National Lab and SLAC believe this is the largest high-performance optical lens ever fabricated. This is the L3 lens. And then there you can get the idea of how large that camera is on the left. That's the largest digital camera in the world. And you can see them installing it on the telescope on the right side. It's absolutely enormous. Of course, the innovation of these pieces of glass are only one small snippet of everything that goes into building an observatory like this, right? So one plug for Drew already mentioned the Corning Museum of Glass. There was actually an event, I believe Tuesday night earlier this week, Connected by Glass, where they had the project manager. He was in some of those photos accepting the blank. He talked about building the Rubin Observatory, as well as one of the directors at the observatory. Very interesting talk. If it's not already up on their YouTube channel, it will be soon. Last I checked yesterday or the day before, it wasn't up on their channel yet, but look for that. Very fascinating talk on how they built the Rubin Observatory and what it's going to be doing. So what's next? So one of the big things that's coming in the next, hopefully 15 years, is the Habitable Worlds Observatory. So NASA is going to be building a large space telescope called HWO, or Habitable Worlds Observatory. That was recommended by the most recent decadal survey that NASA put out. It's going to be the first telescope that's really designed specifically to search for signs of life on planets out orbiting other stars. So there's some key technologies that need to be developed to enable this. So one of them is an ultra-stable telescope. So they've got to be able to detect these faint signals from planets, from distant planets that capture sharp images, right? So they're talking about picometer stability is what they need. The other thing that they'll need is a incredible coronagraph to block out the light from those stars that they're imaging the planets next to. And then they're going to need to develop a more powerful multi-object spectrograph, so they can really analyze the light from those signals from those planets. So one of the things Corning wants to do is figure out how can we help with that ultra-stable telescope. So these are just some of what NASA is calling the exploratory analytical cases, 1, 2, and 3. This is what it's going to potentially look like. It won't look exactly like this. They've actually moved on to EAC 4, 5, and 6 by now. But the one on the right, this is an off-axis 6-meter telescope. This is also an off-axis 6-meter telescope with a different style primary mirror. This is an on-axis. The one on the left is an on-axis 8-meter diameter telescope. So Corning's working on things, continuing to work on things. Of course, we're always trying to improve the way we form glass. I didn't talk a lot about that in the presentation, but trying to make what we call boules that are larger, greater homogeneity, right? So for fused silica, you want the index of refraction to be incredibly homogeneous across that blank. For ULE, you want the coefficient of thermal expansion to be as perfectly homogeneous as you can. So we're always trying to improve that. But in addition to that, we're developing a completely new way to manufacture ULE, and we've called that extreme ULE. So that's going to, or already is, greatly improving the CTE homogeneity. So we're hoping to develop ways to get the size large enough to potentially use that in habitable worlds. We're also developing new ways to improve even further our CTE metrology, how we're measuring the CTE. One of the things that's going to be helpful for them as they're building this telescope is making sure that they understand exactly what the CTE is at any point in that mirror. So we have a good way to do that now, but it needs to be even more precise than it is. And then we're also working on ways, how can we manufacture a lightweight mirror, fuse it together, essentially at room temperature. So that's going to enable hopefully faster manufacturing, greater lightweighting, and improved CT stability. So again, that going back to what I talked about in the beginning, that exploration is driving innovation, right? So the need for exploration, the needs of exploration with, for instance, this next program for Habitable Worlds Observatory, it's driving innovation not just at Corning, but all over the place. And hopefully that innovation is going to enable the exploration to happen. So with that, I guess, does anybody have any questions?
Wow. I guess is in a word. We'll start out with a question right here.
Well, being a baker at home, were we at Goodwill when you found those two? He got very excited because he found two cup measuring cups
Pyrex,
that had Pyrex in big letters, all of it. And I even noticed on one of your early slides that when we were developing ULE, you called it Pyrex with little letters, and supposedly the big letter Pyrex are your better implements to
Yeah, I think the actual Corning brand is with the capital letters. I may have had that wrong in one of the slides, but yeah. So Corning sold that to World Kitchen, I believe. I'm not sure what decade that was. And some of it is using the same borosilicate glass. Some, at one period of time, they weren't actually using borosilicate glass. They were using, I think, tempered glass. And so depending on when it was actually made, you've actually got the good stuff or maybe not the good stuff, unfortunately, still. So, yeah, you can find some nice things.
Wait.
Okay, yeah. Stay away from it.
Especially for high heat applications.
Right, we have another question back here.
Hi, how are you? Not a physicist, so I'm very curious in terms of imaging for dark energy. I know that dark energy is like being looked into as sort of, I guess, like a, and correct me if I'm wrong, but a source of energy production or efficiency. But what specifically are you imaging for to find or locate dark energy?
Yeah, unfortunately, I'm not a physicist either, and I don't actually know how they're looking for it. I don't know a whole lot about dark energy or dark matter other than I think the models of the universe right now, the mass that we can see doesn't explain things the way it's reacting, right? And so there must be some other force that's acting, some energy force or additional matter that's out there, and so they're trying to discover what this is. I'm not sure that they know for sure that they're going to be able to find it with the instruments that they're using. Unfortunately, I don't know exactly how they're doing the imaging. It's a very, very good question, though. I don't know if anybody else does that's here. So folks might know.
Crickets at this point. I actually have two questions. What's your background? What do you?
I'm an engineer. So I went to Clarkson University. I'm a mechanical engineer. So I'm not an astronomer, but I lucked into this role, and this has been fascinating.
So the other question I have is, I'm also not an astronomer. I'm an electrical engineer, but I looked at the thickness of some of those blanks, and what I guess again, weight is obviously an important factor, especially when you're trying to send something up into space. Why are those mirrors as thick as they are?
So some of the older ones, for instance, or some of the newer ones?
Well,
or in general?
Starting with I guess the older ones, obviously they decided that it needed to be that way, and obviously as time goes on, you can work to improve on it. But like we have a mirror blank back here that is about 5 inches, thick, and why does it have to be that thick?
So I think the aspect ratio was a key issue, particularly the older style ways of supporting the mirror blanks. They've improved that drastically. So things like, if you noticed on the Discovery Channel telescope or the SOAR telescope mirror blank, if I can get back to those, are relatively much thinner. It's a much thinner aspect ratio. And so some of these they've improved. Some of them they're actually supported on the back side with actuators, and they're not really adaptive mirrors, right? So they're not pushing and pulling like that, but they're doing something similar to that. Where the older style, I'm not sure how they were always supported, if they were only supported at the OD. And then, of course, for the lightweighted mirror blanks, stiffness is huge. And so being able to have a back sheet improves the stiffness. So one of the ways you can make a lightweighted mirror is by just machining out the back side to make pockets. The downside of that is you don't get the stiffness that you have with a back sheet. But also just the thickness of that mirror blank, the aspect ratio is a huge driver for the stiffness of the mirror blank.
All right. Any other questions? Oh, you have a couple here. Actually, I'll go around this way and then back that way.
First, I'd like to have a comment that I have a 8-inch telescope that I made from a Corning blank that Corning used to sell back in the 1960s and early 70s. There were actually mirror-making kits you could buy with Pyrex mirror blanks. I made that thing myself. But the other thing is I'd like to hear your comments on my personal telescope. I have a 20-inch Dobsonian. It has a fused mirror in it. It's less than 1 inch thick. Two pieces of low expansion glass fused and then slumped into a ceramic mold so that the mirror is meniscus shaped. It's the same thickness throughout, has the same curve on the front and back. Am I going to have a problem with that fusing process with the mirror holding its figure in the future? Or should that fusing in the make it strong enough to hold together and hold, a 1/10 of a wave or 15th of a wave surface on the front?
Yeah, so we've done a lot of mechanical testing on the fusion bonds when we fuse the glass together, and it's just as strong as the bulk glass, essentially. So as long as it's fused together properly, you shouldn't have any problems. It would be the same as bulk glass.
So I guess you'll keep the scope then. All right. All right, get another question here.
Andy, on this slide in particular, the 5 years that's implied, how long does it take to make one of these?
So these were manufactured just at 2 separate times. So one was in 2000, the other mirror blank was in 2005. So depending on the specific mirror blank, it might take, something like this. Could take anywhere from 9 months to 15 months, depending on what else is going on in the factory at the time. A lightweight mirror blank might take more like 15 months to 18 months. Again, depending on what else is going on, how many things we're running concurrently. But of course, then for the finisher to then take it, finish it, coat it, assemble it into an optical telescope assembly, that actually takes longer than it does to manufacture the mirror blank. So that's why you often see some of the delays in the year 2000 to 2003 or 2005 for the Discovery mirror blank to 2012 when it was commissioned. So.
All right, another question?
When they finish the mirror, like what do they use for the mirror itself? Is it a metal compound or what is it?
For the coating?
Yes.
Often it's aluminum, I believe, but depending on the specific application, like James Webb has a very unique coating. I think it's some type, actually I'm not sure what it is, but some type of a gold coating.
I think it's gold.
Gold. So it really depends on what the telescope's being used for, yeah. But often I think ground-based telescopes are a simple aluminum coating.
And correct me if I'm wrong, but I believe on the James Webb, the amount of gold that they used for all of that was, I think, the equivalent of a wedding ring.
It's amazing.
Just a wedding ring's worth of gold that covered that entire.
Yeah, if you think about it, an entire mirror blank that's polished, the only purpose is to hold that coating there in place. Really, the reflective surface is just that very thin coating. So this is really just a support structure, a stable support structure.
Well, unless there's any other questions, Andrew, I want to thank you so much for this extraordinary presentation. It's again, there's so much that goes into everything that we use these days, and the extent that you have to go. I'm also trying to think the amount of energy it takes to just make one of these is extraordinary as well. And so thank you and your colleagues for all the work that you do up in Canton, and we look forward to hearing more about the next mirrors that get installed somewhere, and invite people to also check out the Corning Museum of Glass, which is a great. It's less than an hour away, and you can get in for free with a Kopernik membership. So, just saying. Anyway, so again, we also have a rule here that, well, yeah. So again, if you have any other questions for Andrew, I'm sure you'll be around for a little bit. Although I suppose the family would like to go to sleep at some point. But we have a rule here that you can't leave Kopernik until you look through a telescope, and so we'll invite you to come out into the yard and also out into the domes. The moon is going to be out there, and Saturn should be up as well. And avail yourself of these resources. And next week, our program Friday night will be Fall Skies. What are you going to see through one of those telescopes that you've got? So we'll look forward to seeing you next week and weeks going forward. Or also, yeah, we also have some telescopes and other equipment in our Earth Science classroom that have been checked out at a great price. So if you're sort of in the market, or you think you might be in the market, go check that out as well. Thanks again.